Now we are recording. Please.
Hello, Murat. It says Ergo has entered the waiting room for this meeting.
Host is admitting them.
Pardon?
Host is admitting the people
Okay.
into the room. So there is this waiting room feature now.
Oh, okay.
In Zoom, so they are getting admitted.
Thank you.
Sure.
Okay. Hello, everyone. Good morning. I am the session chair of BlockDM 2020. Welcome to this workshop. And on behalf of our PC co-chairs, Jianliang Xu, Cheqing Jing, and my name is Yuzhe Tang. I would welcome everybody to join this online version of our workshop, BlockDM. So this is the second time for this workshop affiliated with ICD as well. So today we have a program of one technical session and a couple of invited talk and keynote speaker talks. The first speaker is Dr. Murad. Dr. Murad is a professor in computer science department and the director of data security and privacy lab at the University of Texas, Dallas. He received a PhD in the computer science from Purdue University in 2005, where he received the Purdue Series Diamond Award for Academic Excellence. He is also a visiting scholar at Harvard Data Privacy Lab. His research focuses on the integration of cybersecurity, machine learning, data science, and blockchains for creating technologies that can efficiently and securely store, analyze, share data, and machine learning results. His research has been supported by grants, including NSF, Air Force Office, ARO, ONR, NSA, and NIH, and so on. He has published more than 170 reviewed papers in top-tier venues, such as KDD, Sigmod, etc. He has been serving program co-chairs for conferences such as ICD, ACM SegMed Cloud, ACM Code Spy. Some of his research has been covered by the media outlets, including Boston Global, ABC News, etc. He is also a distinguished scientist of ACM. Actually, the accomplishment of Murad has a long list, so I will probably skip that. But without further ado, please welcome Murad's talk, Blockchain Analytics for Fun and Profit.
Thank you all. I was hoping to give a much more detailed talk, but everything is changing because of the online. So I will give a much shorter talk. I hope you can see my screen and the slides. Yeah, so, okay. So basically, I'm going to talk about our blockchain analytics work. It's a joint work with many students and other professors in the department. So since you are in this event, I don't think I need to motivate you for why blockchains are important and why we need to use. But for us, the reason we are very interested about blockchain analytics in general is that this is the first time, I guess, in the history of finance where you could see all the transactions ever happened. So in a sense, if you look at Bitcoin and Bitcoin network, you would have the first transaction where Satoshi Nakamoto created the blockchain or Bitcoin to now, and every single transaction is available there. Also, of course, there are some exceptions, like there are some dark pools and there are some other things, but this is unprecedented openness with respect to the transactions available. So now the question becomes, can this blockchain activity that we can observe on Bitcoin or Ethereum, etc., be useful to detect and predict phenomena on blockchains or even in markets. I'm going to briefly talk about financial analysis, but I will ask you, and I will promote our tutorial on it. We have a tutorial on this topic during the actual conference, so I will only briefly mention what we have done there. And then I will talk about an area that's more, I guess, closer to my heart, which is ransomware detection. So before I go into that, the question becomes how we model the blockchain graphs and how we model all these transactions. I'm just going to talk about Bitcoin today because that was our focus. And Ethereum has a slightly different structure, so you have to change how we model the graph. But if you think about blockchains such as Bitcoin, you would see this graph on the right. So where you will have a transaction. So a transaction will have an input address and it will have an output addresses. Important thing is that you may see 3 Bitcoins got in, 0.8 to go A, 2 Bitcoin go to address B. Of course, what happens, the difference is that the difference in Bitcoin is paid to the miner. So this 0.2 must be, is paid to the miner. Therefore, all incoming addresses and the value associated with those addresses are basically needs to be spent. Here it's 3 Bitcoin needs to be spent. So now what's happening is that you can now create a chain over time. So we have address nodes and transaction nodes. An address node is input to a transaction, and the transaction may have multiple inputs and multiple outputs. Okay, so it turns out that you can mine the structure and you can analyze the structure for multiple things. In a couple of our past work, I list them there, but I will also, as I mentioned, we will discuss them in more detail on our blockchain. It turns out that the subgraph structure of the blockchain graph, especially Bitcoin graph, provides important information with respect to financial transactions. And what we have shown is that you can use what we call K-chainlets, and I will give an example of what it is, but you can think of it as a simple subgraph structure. And when you look at this patterns in chainlets, you can get a much better prediction in the future price movements. So I won't talk about why this is happening in this talk. So please come and see our tutorial during the main conference. Is that basically it looks like the community structure and how the transactions happening has an indication about the future price and popularity of the Bitcoin. And so what's this K-chainlet I mentioned? So this is an example of chainlet. This is a simpler subgraph. So we are simply counting. This is what we call first order chainlets, the simplest one. And you can expand on it. So basically we are looking at, given a transaction, how many inputs are there and how many outputs are there. So this will give us in our thing, first order chainlet of 3 to 3. So this is a first order chainlet. So we look at the number of transactions that have 3 input addresses and 3 output addresses. This is a different type of chainlet where it is 2-3 chainlets. So we have 2 inputs and 3 outputs. So this is first order subgraph in the Bitcoin network. So once we look at these subgraphs and look at the counts and patterns in these subgraphs, we should be able to analyze things. So what we use the analysis for is that we start counting the occurrence and the amount. For example, what is the percentage of occurring in a given day, one-to-one chainlet? So it means that you have 1 address input and 1 address is output in your Bitcoin. So the issue becomes like why this is important. It turns out that when people are spending and using Bitcoin, they have different patterns that are happening. So that way, this kind of shows immediate potential usage in the Bitcoin. And then different patterns are usually, you have seen them, people collect maybe their money in different addresses and then get ready to sell them in the market. So this may have an indication of a potential price drop. So therefore, we show that by looking at these graph patterns, which we call chainlets, in this case, simply we look at how many times some certain pattern, like one input address, one output address, or how many times an input address and m output address occurs, and the amount of money that they transacted to do price prediction. And what we show is that using these graph features improve the accuracy of price prediction compared to regular techniques such as time series analysis. So therefore, these graph features and the Bitcoin transaction graph has an important information about future price movements. Of course, it's not enough us to make rich, so there's still lots of uncertainty in Bitcoin price that we cannot model with the graph structure because many outside information impact the price. But this shows that the graph, our results show that the graph patterns have a good predictive utility for the future of Bitcoin price and financial movements. As I mentioned, we have a tutorial on this. Please come and join us during the regular time and we will go on deeper details on it. Instead, today I will focus one particular piece of work more in the ransomware address. I don't know how many people know ransomware, so I will just quickly summarize it. It's becoming a big problem for many businesses where their data is hijacked, encrypted, and they are ransomed for unlocking it. Similar thing is happening in America. So there are a couple of cities that couldn't function due to a ransomware. These ransomware attacked these cities, they hijacked their, they encrypt their sensitive data and systems. So there were a couple of cities that couldn't process payments for water bills and stuff. So what is this ransomware in more details? Basically, ransomware is a malware that infects victims' data and encrypts it and demands a ransom to release it. And this ransomware also can infect IoT and mobile devices. So we see it's happening that as well. Once the resources are locked or encrypted, ransomware displays usually a Bitcoin address. Nowadays, they are looking into other more privacy-preserving coins, such as Zcash and stuff. But the main issue is that why it's Bitcoin. Bitcoin is much more common, and it has much more stability. I mean, not stability, but it has, you can buy it easier in many cases because many major exchanges such as Coinbase supports Bitcoin. Therefore, it's very easy for you to buy Bitcoin if you are as a company. So the user, the ransomware owners or ransomware developers, you use Bitcoin heavily. And the amount usually depends on the number and the size of the encrypted resources. And it turns out that in many cases, there's actually interesting economic analysis. After a payment, a decryption tool is delivered to the victim and the victim can unlock the data. And it turns out that in many cases, the ransomware people, ransomware developers unlock the data. So now the question becomes, now, as I kind of argued very briefly, that we could use the Bitcoin transactions and Bitcoin network to predict price. The obvious question is, can we use the Bitcoin network and the transaction information to detect ransomware payments? So therefore, can machine learning help? For those who are doing a little bit security on Bitcoin and so on, there were usually heuristics out there to follow ransomware payments. One heuristic is, for example, co-payment heuristic. So usually if multiple addresses are input to the same transaction, in order to make this transaction, you have to sign each transaction. I didn't go because I didn't have time about the fundamentals of blockchain. Again, for those who are not very familiar with the fundamentals, we will go with all these fundamentals, such as how the transactions happens, mining, etc. in our tutorial. You have to sign the address, the transaction. So therefore, if multiple addresses are input the same transaction, it means that you have some control over the signatures usually, which means that those two addresses must belong to the same or controlled by the same entity. So that can be used to, for example, detect some certain malicious addresses and so on. So till our work, there wasn't any detailed trial on using machine learning and especially advanced blockchain analytics techniques to detect ransomware. So what we have done is based on the analysis, we identified important network features. What we call is income, loop, neighbors, weight, count, and length. So I'll briefly explain it to you. So income of an address is that how much of a given address is received in total. So in Bitcoin, addresses are never used. So usually for security reasons, you would change the address. But still, how much came to that address to begin with turns out to be an important indication of ransomware, especially if a ransomware has certain amounts that they are asking. Nowadays, they randomize their amounts a little bit. And then, so the other thing is let's go with A1. The neighbor of A1 is 1. In other words, how many output this address is inputted into different transactions. So, and then we have the length of which is, let's look at A10. The issue becomes here, before I go, let me first mention the count. So if you look at the count of A10, which we look at into how many inputs it comes to that transaction, and that's the basically the count. Also, we have an operation called weight, which is how much of the output is inputted to the one transaction. And so we have these kind of features that we are gathered in the network. So the reason we use those features are that there were certain ways you try to launder the money, and therefore it causes certain graph patterns for those kind of money laundering. So these features are designed to capture those kind of behavior. Of course, the question is, what about other behavior? So since these are very generic things like how many times it's involved in a transaction, how much input is coming, how much of it's going out, those kind of features look like useful for any type of malware or ransomware available out there. And of course, we don't have a proof that it will work for future ransomwares, but that's at least our hypothesis at this point. So the research questions we looked into is like, can these features be used to detect ransomware behavior? Does a given ransomware family show the same behavior on Bitcoin blockchain over time? In other words, is there stability in terms of behavior? Our hypothesis is that once you have a certain type of ransomware laundering scheme is employed by the ransomware, Bitcoin laundering scheme, then they will probably continue. Now, the other question is that what about different ransomwares, different ransomware families where they try to collect the ransomware? Do they have similar behavior? Here, this is the biggest and hardest part of this research. There were some addresses that we strongly believe is ransomware associated, but we have no way to prove them. I will tell you about our data sets. We are so sure about certain addresses, but certain addresses are never being verified independently. So we believe it's ransomware, but we don't have any way to prove it. Still, I will talk about why we believe such a case happens. And the most important thing is that can we detect the emergence of a new ransomware from Bitcoin blockchain? So in other words, if by looking at the transactions, can we say that there is something malicious is happening? Maybe this is the emergence of a new ransomware and the ransomware associated payments. I will, in the interest of time, I'll skip it. Of course, the question becomes, how would you do it? You have the features. Of course, given these features, we can just use standard stuff like a similarity search, like you can just look at the similar patterns in the transactions or addresses. You can look at, as I mentioned, this is what security researchers were doing, which is to look at these transition cost spending heuristics. And then there is also standard machine learning like techniques like tree-based techniques. You may ask, like, why not deep learning and so on? Because the number of features were used is dimension small, so deep learning techniques doesn't require it there. And in our other work, we look at people who use deep learning techniques, and still the accuracy seems to be higher in our scenario. So of course you can do standard clustering techniques, or cluster malicious things together. And then we introduced some newer technique based on something called topological data analysis. So the TDA, this topological data analysis, is basically the fundamental idea is to really extract this hidden data shapes. This is not our development. There's an entire field called topological data analysis, but we basically applied and slightly modified it for ransomware detection. So what we have done is that we apply these TDA techniques to cluster addresses, and based on the features we extracted. So if you look at the clusters here, this shows about relationship between clusters, if there are addresses and so on. And also we show about some clusters. For example, this one here, it has 537 addresses in it. And it has also many ransomware addresses in it that we know it's a ransomware address. So therefore, TDA seems to give us good clusters based on the past data we have. And that's the technique we use to do it. Again, in the interest of time, I'm sorry I couldn't go into details, but again, in the tutorial, we'll go into mathematical details of how TDA would work. So what we have done is that this TDA technique, we applied it on a Bitcoin transaction graph from 2009 to 2018. And we look at the daily transactions and look at the transaction in each day. So basically, like approximately every 10 minutes, we have one block. And every block have certain, because there's a block size and a certain number of transactions. So this way you can process one day at a time easier. And then what we have done is that we get the existing ransomware data set out there. The good thing about these ransomware data sets is that they gather these addresses from actual victims and or running the like a host get it infected by ransomware and look at the address there and send a little bit payment to that address so that they can track where the money is moving. So that's how they learn the addresses. But of course, there may be many addresses that they may miss. So that's what we try to find. Of course, I'll explain why it is. So when we combine all these data sets and merge the addresses, we have 27 ransomware families. Some of them are like a slight variant of the original one and so on. And we have many known such addresses. So first thing we looked into is that what these patterns mean and how well it's ranked in the ransomware. So remember our 6 features and whether they are common in ransomware families. These 6 features, for example, this one is appearing in 300 different addresses, 327, and its all rank is 1 in ransomware. It's the most common in ransomware, and it's also the most common in the regular transactions as well. So this doesn't show too much differentiating factor between ransomware and the regular one, because although we see it in ransomware, it's also seen in general in Bitcoin. But if you look at this pattern, this one, it's very common in ransomwares, but it's not very common overall. So it is 113 overall. So the implication is that it is not super common. And it turns out that certain payments, most payments have this type of behavior happening, which is that it looks like a person who's paying ransomware collects money from different addresses and either pay to one address or at most to two addresses. And these features are try to capture these things. This is showing, like, for different features such as count and loop features, how the distribution happens in the white addresses. White addresses means the addresses that we are known to be non-ransomware related, and the left ones are the ransomware addresses. We can see that the distributions are slightly different in these two ransomware versus non-ransomware. This is our TDA technique based on different clusters. So there is this sensitivity feature in it, and by playing it, we can adjust the clustering. So basically, what we know based on the known addresses, we can arrange the number of clusters, change the number of clusters. So this looks like an optimal point where we get pure clusters, which means that clusters are mainly or highly concentrated non-ransomware addresses in it. Of course, we done and compared this TDA technique we developed, topological data analysis based technique we developed with the baselines. It turns out that the naive approach, such as doing similarity, cosine similarity, worked kind of well to detect some ransomware patterns. But the problem with this naive approach is that it has many, many false positives. So at a given date and addresses, it will create many false positives, which would be hard for the law enforcement and others to check the details. The nice thing about the TDA is that we can play with the sensitivity of the clusters. Remember, this is unsupervised way of doing things. So what we were doing is that we cluster using TDA, and if the cluster has a majority known ransomware in it, we label that cluster and addresses in that cluster as potential ransomware. And by playing with sensitivity, we can obviously change precision and recall values. Of course, recall turns out to be high, but precision is not super high. So that's always the criticism we got in our reviews till we got accepted. The argument is that the precision looks lower. But the main reason is that there are some addresses we never known to be ransomware. We believe they are ransomware, but there's no way else to do it. But furthermore, the important thing to note is that this is a significant improvement compared to heuristic-based techniques the current researchers are using and the startups are using in the wild. So that's, although the precision as now looks low, this is a significant improvement, and of course we are trying to improve it even further. So for different ransomware families in this graph, I have a few minutes left, so I would not go into too much details. We look at the TDA technique we developed and the technique that is the most closest in terms of performance. So as I mentioned, we tried 6-7 different baselines. So for each family, we look at ransomware and so on. So basically, we can find the new ransomware addresses. So the way we did in these experiments is that we know the addresses till, let's say, certain time frame over the development of the ransomware and see whether we can predict further ransomware addresses in the future. So in every case, TDA turns out to be better. And in terms of false positive problems, for every true positive, we had 17 false positives. That's the reason precision is low. But this is much better than all the other non-TDA techniques out there. It turns out that we can also even predict new families. In other words, can we predict an address to be ransomware, even if we have seen no addresses associated with that ransomware? So it's possible to do that with some accuracy, like we mentioned that it's for cryptxx, and we detected the emergence of a new ransomware, cryptxx, before the others. So the issue is that, of course, it looks like there's also false positives. In order to limit that, we also develop further heuristics where we eliminate certain chainlet patterns. Because as we mentioned, it looks like ransomware is focused on certain chainlet patterns for obvious efficiency reasons, because it shows only one address to begin with to start the chain. So we can remove certain type of chainlets. There's something called multi-sig addresses, which is rarely used in ransomware, because ransomware is controlled by one person, usually, or one entity, so it's not there. So once we do this kind of elimination and remove the things that are known, we managed to remove some of the predictions and make it more useful. So by using this address elimination, we discover 324 addresses that we believe is suspicious. And these addresses, 3 addresses appear in 6 time windows each, which means like 6 different days. We find, further this, we find around 350 suspicious addresses. And we know later analysis revealed that by these data sets through addresses. We believe the others we found is also a ransomware address, but as I mentioned, due to the limitations of getting ground truth, there's no way we can prove this. So that's like one of the biggest challenges for checking your techniques out there. But we are exploring collaborations with some companies who have other sources to verify the ground truth. So this way, hopefully, we could do that. So I will stop here, saying that blockchain graph features have important implications for detecting financial movements and analysis and ransomware detection. And thank you for attending. I think I have a minute or so for questions. We have a survey on the blockchain from graph and analytics point of view. As you will hear, talks today on system and other aspects. And then I'll stop here. And as I mentioned, we also have a tutorial during the main conference. Please do attend for further details. This is just, I would say, preview of the area. Sorry, yeah, please go ahead. Yeah. Are there any questions?
Yeah, thank you. Yeah, I saw one question so far posted on the chat. So I think the audience is interested in knowing the detection result. After this, what happens after this work? Now we know who are the ransomware and which transactions are related to ransomware. So is there any way, any use of this information?
So basically, the next step is going to unfortunately, to the government. So we are trying to sell this work to Department of Homeland Security. So they have to really take over from these addresses, and they need to follow up with exchanges and so on to verify. Because at the end of the day, at one point, these addresses are converted to basically fiat currency, whatever that fiat currency is. Therefore, it requires government access to do that. The second thing this is useful is that you can estimate the ransomware prevalence and the amount of ransomware paid. So therefore, you can estimate the economic impact. Of course, this would be a rough estimate because, as I mentioned, we may have some false positives, but it would give us a nice, I would say, range about how ransomware, how prevalent is ransomware and how much is paid in general. Because some companies and some organizations don't disclose what they pay to ransomware operators.
Yeah, and also, can this information be used to prevent the future such attack?
I think, of course, not really, because the ransomware is usually happening at the malware level. Therefore, you know, if someone found like one of the most common ransomwares, this CryptoLocker, was exploiting some vulnerability in Windows, and they were lacking many companies. So as long as those vulnerabilities exist, ransomware will exist. But if the operators of ransomware can be caught, or at least their transactions could be prevented, they may have less incentive to run the ransomware. So currently it's a good way to make money easier when you do hacking. So if you attack their financial mechanism to launder it, I think it may prevent future ransomware developers to launch ransomware or de-incentivize them. If there are no further questions, I'll stop sharing, and I think Latifer will take over.
Yeah, I also have a question. I was waiting for the audience, someone to speak up. But in case there's no, so I have a question. Like in your case, you mentioned about one of the difficulty is to get the ground truth, right? But if you think about from the ransomware developer or author's perspective, he has to post Bitcoin addresses in order to receive payment, and along that,
then combine them,
include some context. So this is you are being attacked by ransomware, so you have to. So is that piece of information being considered in your work?
Not really. We just look at the ransomware transactions and the Bitcoin transaction graph. We don't look at any other information. So if you think about it, now you may ask how the others find out these addresses. One trick that people have used is you run a honeypot and let it infected by a ransomware. And then when ransomware discloses an address to you, in the early ransomwares, they were stupid and they were just using the same address. The newer ransomwares create a unique address for you. So therefore, you cannot just use that address to track things. So because it's a unique address for you. So one trick people have done is to send a small amount of payment to that address. Because ransomware developer usually aggregate it and move it around. But then what happens is that now they don't fall for it. Now, if you just send a little bit Bitcoin, they are not touching it anymore. So that's how they learn. That's the reason these kind of anomaly detection techniques are becoming even more important, we believe. But of course, we need government enforcement collaboration, and that's what we are trying to work on now.
Okay, if without any other questions, if there's no other questions, I would like to virtually thank Murat's talk.
Thank you for attending.
Yeah, and the next, yeah.
So yeah, I'm on the line here.
Yeah, hi. Yeah, the next talk is automating vulnerability detection and prevention in smart contract. This is from Professor Latifa Han, also from UT Dallas.
Thank you. Thank you, Richard.
Yeah.
Can you hear
me?
me?
You want me to briefly introduce yourself? Just one or two. Dr. Han is currently a full professor in computer science from UT Dallas. He is ACM distinguished scientist and received IEEE Big Data Security and the Senior Research Award. He is also a fellow of CIRI. He has published many papers, more than 3,000 papers in top database and other conferences and other fields. Currently, his research is focused on big data management and analytics, data mining, and its application to cybersecurity. Without further ado, let's welcome Dr. Han's talk.
Okay, thank you for a nice introduction, Richard. Can you hear me?
Yeah. Okay.
So my talk will focus on the smart contract vulnerability detection and mitigation. This is the work was, some part of the work was done by Debu and Mariam. Both of them graduated and working. Debu is working in Google and Mariam is working in Walmart lab in Silicon Valley. So, so in this talk, I will focus on the two things. One is the detection, the other one is prevention in the context of smart contract. So what is a smart contract? Smart contract are autonomous applications that execute in a decentralized virtual machines. And the smart contract is developed using a new programming language called Solidity and Haskell. These are very similar to JavaScript. And since smart contract becomes very popular, so even the Google acquired a startup. So you can see from this slide. And then since it becomes very popular, adversary wants to exploit that and exploit the vulnerability and causes financial loss. So here are some examples that you can see. Ethereum is one of the widely used blockchain systems. So their smart contract has been utilized, and by exploiting the smart contract vulnerability, this amount of financial loss happened. Now, before going to talk about the more details about the detection and prevention approaches, so I just want to introduce you some of the background information. Then I will move towards detection, and then after that I will talk about prevention technique. So what is smart contract? One of the widely used blockchain system is Ethereum, and Ethereum uses smart contract, and Ethereum exploits the virtual machine. The virtual machine is a stack machine. It uses 116 instruction, and it consists of two memories, permanent storage and the volatile memory. Permanent storage where the data will be stored, and the smart contract data may be stored, and the volatile memory where the program execution can happen. As I told you, that in order to do the smart contract programming, new programming language has been developed. And this is since it is a relatively new programming paradigm, so there is a lack of security standard. And furthermore, for the source code level, developer utilize special libraries like SafeMath library. Here is some sample code. So here we try to avoid the overflow situation by utilizing this type of SafeMath library. But it's still when you write the code using the for the smart contract using the Safe library, there might be possibility that some vulnerability may exist. So here's some sample examples. Here expectation is this message sender should be the owner of the smart. Okay, just give me 1 minute. Okay, so it should be the owner of the smart contract, but the condition in the code below allows non-owners to access the smart contract, so that may open the door for vulnerability. So what I'm trying to say here, smart contract is not a traditional normal program. It is self-executed, and it is one-shot programs. So you cannot patch it immediately because we use some sort of signature. So we have to recalculate the hash. There's some issues, so we cannot do this one. And new programming language is introduced to write the smart contracts. And furthermore, when you let's say in this work, first I want to talk about the detection technique for the vulnerability detection for the smart contract. So there is a possibility that the smart contract code may not be always available, the source code. So what we have which is the bytecode. And from the bytecode, we want to, since the bytecode, it is possible that we may not get the source code. So what we can do? So and furthermore, we can convert the bytecode into some sort of assembly equivalent code and do the analysis. But we cannot do the manual analysis because we have too many of this type of the assembly code we have, or we may consider a lot of smart contracts. So we need to come up with some automated method. This diagram motivates that. So y-axis represents number of smart contract, and x-axis represents the timeline. So you can see with the increasing time, for example, in the Q1 2018, we have more than 500,000 smart contracts. So the number increases exponential, very high rate. So therefore, if you want to do some sort of detection, whether the smart contract is vulnerable or not, so in that case, we need to come up with the automated method. So for that, we're going to use a machine learning technique. So the goal here in the context of smart contract vulnerability detection, our goal is to automatically detect vulnerable smart contract using only the bytecode rather than the source code using the machine learning approach. So again, we assume that source code is not available. So we'll rely on the bytecode, and using the machine learning, we will detect this vulnerable smart contract. And then, then we will show you, so this part is more detection. And for the prevention, I will show you how in a certain vulnerability case, how we can insert the additional guard code so that the vulnerability can be, some of the vulnerability can be avoided. So that's my second part of my talk. So first part, I want to focus on the first part, the vulnerability detection. Let's talk about that more details. So what I said, we will first focus on the vulnerability detection, and then later we'll talk about the mitigation. So there are a bunch of various types of vulnerabilities exist. So in this work, we only focus on the 4 types of vulnerabilities. For the first one is the transaction ordering dependency, timestamp dependency, mishandle exception, and the last one is this. So transaction ordering dependency, miners may reorder the transaction such that outcome is not favorable to the users. And then, so these are the 4 types of vulnerabilities we'll consider in this work, but there might be more. And since when you do the experiment, we got only this 4 types of vulnerabilities or attacks we consider publicly available. That's why we consider this. And time passes, we may have more vulnerabilities. So I believe we can extend our framework to handle those also. Since we apply the machine learning technique, so this is the basic framework. The idea here is in step 1, we have the smart contract bytecode only. We don't have the source code. So in step 2, we will disassemble the bytecode using some publicly available tools. So that will generate some assembly equivalent code. And then from there, we will generate then we generate the control flow graph from here. And then from this control flow graph, we will end up with a vector representation. And then we will have each of this so we will have the machine learning technique. So supervised learning technique will be utilized. So we'll have the training data. So in this case, the vector representation for each of the smart bytecode plus the vector representation we will generate. And then we have the label data, whether it's a benign or malicious. And then we train a classifier. So in this case, we'll not only use our neural network based classifier, but also we exploit traditional SVM and the k-nearest neighbor, and plus we exploit the distance learning. So I will talk about those little bit details in a minute. So, but let's walk through these 3 steps a little bit more details. So again, this is the original bytecode you have, and from there we disassemble the bytecode and generate some sort of assembly equivalent. And then from there we will need to extract the features and represent them as a vector. So we will, in the intermediate stage, we generate the control flow graph, and then control flow graph will be converted into a vector. So let's discuss those steps in details. So here is some simple example for Fibonacci numbers, and the code is written in Solidity. And we still recall that we don't have the source code, we have only this bytecode. And so when we use the Ethereum disassembler, it will, from this bytecode, it will produce the assembly equivalent code like this. So here we're saying push 1, and these numbers will be pushed. So here X is a hexadecimal representation. We're trying to say 60 is the push instruction, and we are pushing the address 60, number 60, and then the next instruction also push, and then 40 will be a push into the stack, and then after 40, 52 is the M store. So this way, the disassembler will generate the opcode plus the operand or the values. And then, so from there, our goal is to generate this instruction set. We want to generate the control flow graph, and then from the control flow graph, we want to convert it into a vector representation for each of the smart contract bytecode. So keep in mind that we want to construct a control flow graph where the graph will have the node and the edges. So the node will be represents the basic execution blocks. So in that case, you can think about a contiguous number of those instructions are placed one after another, or will be executed one after another, that can be those set of instruction may form a block. So for example, in this case, there is a jump instruction here. So up to this, you can say from here all the way to here, whatever the instruction we have, those will form a block 1, something like this. So here we're saying 0x0 means it starts from 0x0 address, and whatever the instruction we have all the way to 0 before this, it will be treated in this block, all this instruction. And then if there is a jump happen, then new block will be created. So that way we will construct the graph. So once we have the graph, you can see here 0x0 will be expanded internally like this. So now, so if you have any question, you can interrupt me any time. And then keep in mind that we have the smart contract control flow graph like this, and from there our goal is to generate the vector, right? So, and then in this graph, each of this node represents a bunch of instructions. So what we do here, we do a depth first search to traverse the CFG node and extract the operation names in the DFC path. And then, so what I try to say here, so we will have the control flow graph somewhere here, and one of the node in the graph, the first node is this instruction. So we will, and each of this push mstore division will be replaced by numeric numbers. So when you convert this graph, we will traverse the graph in a depth first search. Once you traverse the graph in a depth first search, we will represent them in a sequence, and that sequence, each element in the sequence will be a block or address. And then internally, each block represents a bunch of instruction like this. So we will expand that, and that will be represented by those numbers. So in this representation, we ignore the operand or the values. We only focus on the opcode. And there is a possibility that some graph so each graph, each smart contract now will be represented as a after graph transformation, it will be represented as a vector like this, and we will take the first L.
Let's for a quick question. So when you go over the paths, you have different paths. You concatenate them.
Yes.
Okay. You just okay.
Yeah. So let's say. Yeah, let's say you do the depth first, as you'll come here, and then after that you will concatenate them, the whole path, and then eventually we'll discard. Here, what we do, we take the we have some threshold-based approach. So yeah, the L length we will consider. So we may ignore the last number of representations here. So that way, always we keep the vector length and L. And if there is a if some representation or smart contracts representation has less than L, in that case, we do some padding. So that way now recall that we will each of this bytecode, smart contract bytecode will be represented as a vector. And we do, in our case, we divide that the data set into 80-20, 80% for the training and the 20% for the testing. And then for the training case, it will have the label. So we'll start to train the classifier. So in our case, we use some new approach to train the classifier, what we call it metric learning. And this is work we published last year in World Wide Web. So the idea here is, so it's some sort of distance learning. Let's say the positive class in this case represents the vulnerable smart contract, and minus or malicious, and minus means a benign case. So in the original space, when you represent those points, or the smart contract as a point, in the original space, the positive class are far away. These are the same class points, but the dissimilar class points, positive and negative, they are close in the origin, which is counter intuitive. So what we want to do, we want to learn a distance matrix or metric learning, where the same class points will be close together or will be less than some threshold, and dissimilar class points will be of higher than some threshold or above some threshold or far away from each other. So that we want to do, and for that we take a triplet based approach. So in the triplet case, xt is the anchor points, and this is a positive class and negative class, and we calculate the loss. So in this case, from the same class loss and then the dissimilar class loss, and do the optimization using this. More details you can find in the paper. So we exploit that in our experiment. For the experiment, we use this is the 2019 data set. Up to 2019, we collected the smart contracts, and some of the smart contracts are duplicates, so we get rid of this. For the labeling, we rely on this tool, and you can see here the distribution. This is a highly imbalanced data set, so 88% are benign, and the rest of the 12% are vulnerable. And then when we do the 80-20% split and do the prediction, so we use our distance learning. That gives us a very high accuracy, 88%. And when we don't do any distance learning, we observe the accuracy like this. And here we don't do any distance learning. And we also use by LSTM because it's a sequence data, so which gives us a very close result also. So now I want to talk about the second part, the mitigation. So that work, there are vulnerabilities happen due to the overflow, underflow, and overflow, underflow are associated with the addition and the subtraction. And there are other cases. So in this work, we only focus on one type of, two types of vulnerabilities, overflow and underflow case. So now our goal is to make sure that when we encounter this underflow or overflow, we want to have, fix the code. So we want to add some guard code so that this overflow, underflow will be entirely avoided. But in order to, when we add the guard code, the problem is the original, in the code, we have a jump instruction. So jump some particular target address. So in that case, we may, once we add some guard code at on the top, so there might be possibility that we may need to make changes in the target address. So that's one challenge we face. And then another challenge is when we add this guard code, it will add some additional overhead. In this case, overhead will be stated in terms of the code we are adding. And then add those lines of code, guard code, we need to make sure that this bytecode semantics will be preserved. So we have to verify the bytecode correctness. So the architecture we utilize here, we will have a policy. In this case, policy, we focus only two types of vulnerabilities, overflow and underflow. And we take the EVM bytecode, and disassembler will disassemble it. And then from the bytecode, we will utilize the rewriter, our program, and find and then insert some guard code there. And then we need to make sure that this code is semantically produce the correct result of the original code. So that way we proceed. And so our vulnerability protection approach, we identify the vulnerable smart contract opcodes like add and sub we focus on, as I told you. And we rewrite the bytecode by inserting guard codes before the vulnerable opcodes and identifying and relocate all jump target locations and verify the rewritten bytecode. So that's the main idea we exploit. And in case EVM, the jump can be done this way: jump, unconditional jump, jump, conditional jump, jump destination. So here is a simple example. Say, let's say you have a vulnerable code, add or sub, and then push 106 and then jump. So here the problem is, and we when we modify, when we insert the guard code here, so keep in mind that this address will be changed. So in that case, this address needs to be modified. So we handle those issues. And then I said we have when we add this guard code, it will add some overhead. So our goal is to reduce that overhead. So for that, what do? We just, instead of inserting the guard code every places, we just, that way the inline reference or many guard code will be inserted. So the code size will grow. So we want to control the code size. So what do? We just create a guard code function and call that function. So here, for example, we push the current address, then push the guard code in the virtual stack, in the EVMs of virtual in the stack, and then jump. So in that case, that way we will just call the guard code will be managed with a minimum number of instructions. So that type of thing we observe, and then bytecode verification, we utilize this. So we downloaded 2 million smart contract, and from this we observed that this number of unique smart contract we have, and then we randomly choose this and do the experiment. So we observed that in terms of the overhead, for the overhead is when we don't do any optimization, like not the function, make the guard code as a function. If we don't do it, then overhead is very high. So minimum overhead is close to 10% or something, and highest overhead is close to 500%. But when we do the optimization, do the function call, in that case, overhead drops significantly. So, and as a future work, we for the mitigation part or the prevention part, we focus on the two types of vulnerabilities, the overflow and underflow, and each of these vulnerabilities will be associated with a single with a single opcode like add or sub. But there might be we have more types of vulnerabilities, so we have to extend the work in that direction. Then it is possible that vulnerability may exist more where we will exploit more. The adversary may exploit more than one instruction. So in that case, how we can do that? So that part needs to be addressed. So these are the things we want to address in future. So that's it.
Yeah. Yeah. Thanks for the talk. While we're waiting for the audience to pose questions, I do have one question about the detection part of the work. Like, so you said basically the idea was to use a machine learning algorithm and to sort of expand the training set to discover new vulnerable smart contracts, right? Mm-hmm. So in this case, is there any alternative approach? Like if we can use ONT, that static program analysis tool, to label the training set by itself, can we just, is it possible to use ONT to also detect the vulnerability in the testing set as well? And how, you know, in terms of...
if you see, when I report the result at for the detection, we said that we have this number of smart contract and bytecode, and then we use that tool to level it, because there are so many smart contract, right?
Yeah. Yes.
So we use these tools for level it, and then if this tools gives that this is benign and this is vulnerable, then we will rely on that level. Mm-hmm. But if the tool makes an error, then yeah, then no way we can figure it out. So for the ground truth purpose, we rely entirely on this tool. But you are saying using this tool. So our method is some sort of a static analysis, because the feature we extracted, that's purely based on the static analysis. We rely on the control flow graph, right? Mm-hmm. And then, but it might be better to say the way I discussed the approach is we train with 4 types of vulnerabilities, and then train it and then test it only on these 4 types of vulnerabilities. But what we observe in a different set of work, let's say if the new types of vulnerability discovered? Can we, using machine learning, can we find it? Usually typical machine learning case, some cases you can, some cases you may treat them as a benign case. So that's why what we observe when we do the distance learning or metric learning, there is a possibility that benign case will be well separated from the malicious or vulnerable case. So in that case, if the new vulnerability is discovered and or is found, and it is somewhere in the middle, then the distance learning can detect that well as compared to traditional machine learning. So that way, what we observe in our recent work that we can find zero-day vulnerabilities or zero-day attack better when you exploit the typical metric learning or distance learning. So in other words, when you have outlier situations, you train your models with the existing attack classes and existing benign classes. Now new attacks are emerged, and using distance learning, I think you can find better than the traditional machine learning where you don't exploit as a distance learning or metric learning.
Yeah. That makes sense. Thank you. Okay, if without further questions, let's thank Dr. Han's talk. And
thank you, Dr. Tang.
Yeah, and next we have 10 minutes break. So now is 9:33, and we are going to resume around 9:50 a.m.
Thank you. So did you face any problem with the password? Every time the machine asks me the Zoom, when I click in, they ask me password.
I think so. Initially there was a password, but if it.
But when you started the session, it okay.
If the meeting already started, so then it does not require password. Okay. Yeah, so I think from now you can just join, but probably there is an admission process.
Yeah.
That is
stay on the line and come back. Just mute yourself and come back. Basically.
Okay. Thank you, guys. Bye now.
So, hi everyone. So welcome back. I'm Jian Xu, co-chair of this workshop. Very nice to see many friends online here. And we have about 100 audience. It's very amazing. So now let's move on to the keynote session. So for the keynote, we are very honored to have Professor Abadi to talk about blockchains and databases. As many of you know, Professor Abadi is a professor of computer science at UC Santa Barbara. He is an SM fellow, AAS fellow, and IEEE fellow. He has served extensively in our database community in various capacities, including journal editors, conference PC co-chairs, VODB endowment board members, and currently he's serving as TCD executive committee members. And his research has impacted many areas in databases and also in distributed systems. And he is also a pioneer in blockchain research. So without further ado, I pass the time to Professor Abadi.
Well, good morning, and thank you for inviting me. I would have really liked to see you all, but in this Corona time, we have to distance ourselves. We have to use masks and not see each other. So I hope, but I understand that like this, we have a lot more people and much more international attendance. So this is really, I would like to thank the organizers for inviting me. And without further ado, I can start giving my keynote presentation. So this talk will be about the interaction between blockchains and databases. And I really think this has been a great opportunity and for us as a community to launch into very interesting techniques that overlap some things that we've been working on for years and years from the 60s that are now becoming very prevalent in the context of blockchain. Blockchain, as you all know, has both permissioned and permissionless types. And I believe that both of them introduce very important and relevant challenges that are faced, that can be addressed, especially by the database community. There are lots of people who can work on this and have been contributing to this. Needless to say, the cryptography and the security communities have really presented a lot of the foundational stuff. There's a lot of fundamental research in distributed systems that has contributed here. And I think databases should be launched and should really work on both. Not only, I know the focus has been a lot on permissioned blockchains in the database community, but permissionless, as we saw from this morning's talk from Murat and others. There are really fundamental problems that we can address that I believe others cannot address. Obviously, I should acknowledge my colleagues. This work wouldn't have happened without my continuous collaboration with Professor Divi Agrawal, who we've been working together for the last 30 years. And there are contributions here by various students of mine, Mohammed Amiri, Sujaya Maya, and Victor Zakhari. Victor has graduated and is now actually working in Oracle. So I will give you, the plan for the talk is to go through a sequence of different ideas that span both permissioned and permissionless blockchains. But there are two underlying themes that I want you to have at the back of your head while I'm talking. And I will try to remind you the context and where these things come in, but I hope it will be clear. The first one is that there are database ideas, concepts that have been developed for the last 3 or 4 decades. And there are very novel, interesting challenges that are being posed by blockchains that were just developed in the last 10 years. So there are these two different wealth of information and context. And what I'm going to try and show you is that it's a two-way street. Both ideas in database, and that is what most of the talk is about, is focusing on contributions that databases can do to blockchain development. But there are also some ideas that can come up from blockchains and go to the database. We are just scratching the surface on this latter part. I hope at the very end of the talk, I'll have a chance to give you some glimpses of what we've been doing. Of course, this is all happening within the context of a large distributed system. Blockchains are large distributed systems. It's not only just any distributed system, it's a global distributed system, especially when I think about permissionless blockchains. They are spanning the entire globe. So a lot of the ideas are coming back and forth, but we need to have a deep grounding in some of the foundations of distributed computing that are going to help us solve some of the problems that we face. The other theme has to do with failures. Traditionally, databases especially have been working in a context where we assume that failures are crash failures. So a machine fails by stopping. And we've basically developed many good algorithms and protocols that have been used assuming crash failures. What blockchain especially does, but this is also an idea that has been around, especially in the distributed systems community and obviously in the crypto and security world, that we cannot necessarily trust the infrastructure. There is malicious behavior that can happen. In the distributed systems community, we call this Byzantine failures, etc. So it's not, but the database world has traditionally focused on crash failures, on fail-stop failures. That was what we usually meant by fault tolerance. In this new world, we have malicious Byzantine failures. So those are two themes that I'll be playing around with: crash versus malicious, and then ideas from databases going into blockchain and vice versa. To set the context, let me say some obvious things. But as you'll see at the top of the slide, we have, I'm going to try and put a meme here that will indicate the context in which. So traditionally, our banking systems, we assume that they were crash, and we basically transacted with each other by going to my bank, and you go to your bank, and then a transaction happens in between these different banks. In the worst case, a crash might happen, and traditional good database techniques have been developed to solve these problems. However, what Bitcoin does is it says, no, we are not going to have this big institutions that are really solid banks that we all trust. And remember, banks are usually built, you know, in the center of the city with big columns and look very impressive. They exude trust. We believe in them. We can give them our money and trust our money with them. However, what Bitcoin does is it says, let's replace this bank that is trusted by by everybody to a distributed peer-to-peer network of everybody. We have 100 people here, or maybe at the moment there are 103. You see, people can come in and go out. And we are all collectively, and look, now I cannot necessarily trust everybody in this 103. I don't know everybody in this room now. I'm talking to a bunch of people, and yeah, I know I can trust a lot of you, most of you, but there is an issue of trust that has to be embedded. So this is one of the main concepts that were developed with blockchain. Basically, and you're all familiar with this, is a blockchain is a chain, a linked list of blocks that are connected, where each block has a bunch of transactions, and these transactions are connected not by hashes, by hash pointers. By hash pointers. And this ensures that I have a tamper-free. Why do I need it to be tamper-free? Because we are going to have a copy of the blockchain with everybody in my peer-to-peer network. They are not necessarily trusted. So I need to embed within this structure instruments, techniques, tools that will ensure that it's tamper-free. One of them is the hash pointers. Other ones are, for example, digital signatures, etc. Once I have a linked list that is distributed among a potentially unknown number of participants, and that's in a permissionless world, that's what we assume. To make any progress, I need to add a new block to the end of the blockchain. So what do I need to do? I need to get agreement or consensus among the participants so that if I want to add a block to the end of the blockchain and Jian Liang wants to add a block to the end of the blockchain, only one of us can do it, because otherwise we'll get into a problem. This is a very old traditional problem that has been addressed in the distributed systems community and is known as consensus. And consensus is typically solved using message passing and communication. What Bitcoin did, and this brings me to the first half of my talk, where I will focus on permissionless systems. So in a permissionless systems, we have an unknown number of participants, All of the consensus protocols that were developed historically from the days of Lamport, when he proposed Byzantine agreement, assume that you know n, and that part of knowing n, the number of participants, as a result, you can take a majority, you can take 2/3 majority, you have the notion of quorums, but all of it requires communication. When I am in a world where I don't know the number of participants, I even don't know who is participating, we have to replace the notion of communication and consensus and use this new idea of mining or proof of stake. I will, for the purpose of this talk, at least work with the Bitcoin model of using mining. So what happens here is we replace communication with computation. You are going to solve this puzzle by yourself. And once I solve it, I am going to be able to win and declare I am the leader, and I'm going to add things. This is different from the consensus, where typically we communicate with each other until I get enough participants to agree that I should be the leader. So within this permissionless world, we've been working on several problems, and I've picked one recent one that we've been talking about, which is atomicity across permissionless blockchains. Obviously, you are all familiar with the problem of atomicity and commitment in a database context. So let's move to the permissionless open world, untrusted world. And again, always I try to put this icon at the top to kind of remind you the context in which I'm working. So as you are all familiar, the landscape of cryptocurrencies has been exploding. There are lots of cryptocurrencies. There's Bitcoin, there's Ethereum, there's Litecoin, there are others. And here is a list of them that we picked a few months back. There are over 2,000 cryptocurrencies. Maybe by now there are more, maybe less. And there's a lot of money involved in these things. So people have coins and currencies, cryptocurrencies in different blockchains. So let us look at a problem called the cross-chain transaction problem. And here we have Alice and Bob. Bob has some Bitcoins and Alice has some Ethereum, some Ether. And what they would like to do is they would like to exchange them. So they've agreed among each other that Bob is going to give his Bitcoin, X Bitcoins to Alice if Alice gives him Y Ethers, or vice versa. So what we would like to do, and remember, these are two different blockchains. I'm simplifying the problem. I'm assuming both of them now support smart contracts, etc. So what's important here is I have two different blockchains, and Bob has X in one of them, and Y has Y, as Alice has Y in the other one. And what we would like to do is we would like to change the ownership. So we'd like to develop a protocol that will change. Remember, each of these blockchains has its own currency. So it's not like I'm going to take Bob's X Bitcoins and put Alice's Y Ethers in that blockchain. No, I'll change the ownership. So the ownership of the X Bitcoins of Bob are going to be given to Alice, and atomically, I should swap and give the Y Ethers of Alice to Bob. So this is a problem that was proposed earlier on in 2013, actually, by Nolan And as is typical in a lot of, especially of the permissionless blockchains world, is that a lot of this information is not published in illustrious conferences like ICDE or Sigmod or VLDB. They are published in blogs or comments. And this is what Nolan did. He proposed a very simple solution and in a very specific context. Fast forward 2018, Maurice Hurley took this problem and acknowledged Nolan and generalized it and presented a very nice general solution. So what I'll start my talk with is give you a brief summary of that solution. So here again, we have Bob has some Ether and Alice has some Bitcoins and what they want to exchange. So what they're going to do is Alice is going to create a secret S that only she knows. She's going to hash it using a known hash function. So capital H is known. She's going to hash the secret and generate the hash of this, which is lowercase h. She has now two pieces of information, a secret that only she knows and H, which is the hash of that secret. And she's going to put a smart contract. In a smart contract, she's going to put this, she's going to put her X Bitcoins into the blockchain and is going to say that it's going to be available to be given to Bob if Bob provides the secret. That corresponds to it. So if Bob provides the secret S, so that the hashing of S is equal to H. Of course, Bob doesn't know S, so she can put the money in. So what she's going to do is she's going to take this transaction, she's going to put it in the Bitcoin blockchain. This is going to be visible to all. Bitcoin blockchains are available. Everybody can have a copy. Everybody can see it. Who can see it? Bob. Once he sees this, what does he see? He can see the H. He doesn't know what the hashing, what the secret is, but he knows the outcome of the hashing. So what he can do is he's going to say, I'm going to create a transaction that moves Y Ether to Alice if she provides the secret, and this particular these Y Ethers are going to be locked using the H. And what he does is he puts it in the blockchain to be visible to all. At this point, who knows the secret S? Alice knows the secret S. So Alice can immediately expose the secret S and reveal it and get the ethers that are blocked in the ether to her. So she can get it. But once she has done this, S becomes visible to all. And in particular, it's going to be visible to Bob, and Bob can now use it to get his money, his X Bitcoins out of the other blockchain. So I hope this is clear. So basically, there is a transaction, there are two transactions, and there is this transfer of information based on a secret. Why do we need secrets? Because Alice and Bob don't trust each other. So we really need to make sure that they can do this in an environment where they don't trust each other. Well, unfortunately, this very simple, naive protocol has some problems because Alice's X Bitcoins are already blocked now in the blockchain. Once she puts it, she's relying on the fact that Bob is going to do something in his other blockchain to give her the money. But Bob might see T1 and refuse to do this transaction. He might just say, hey, I'm not interested. I renegated on my agreement and I'm going to go away. Now, what is the problem is that Alice's Bitcoins are blocked forever because she put it in the blockchain and the blockchain has this money, her X Bitcoins are stuck in the blockchain forever. So that's not good. Well, Nolan comes up with a solution, which is the idea of time locks, which is, again, an old idea that we've been using in databases and in operatings for a long time. basically, in addition to the small transaction that we had before, what we're going to do is we're going to say, if the money isn't used in a certain amount of time, and in Nolan's original description, he uses actually 48 hours, which is kind of interesting. So he gives, you need to give time for the other participants to react. So it takes time to put some code, some transaction into a blockchain. It takes time for it to propagate through the network, etc. So she puts this time lock, which is going to say that if Bob doesn't react quickly enough, I'm going to get my money back. Not only that, the same story that I just described could be reversed, and Alice might also trick Bob. So what we're going to do, what Bob does is he says, refund the money to me back if Alice doesn't take the money, and I will need 24 hours. So it's interesting that there is this relationship that Nolan had between 24 and 48 hours. There needs to be a connection between the two different timeouts that are being given. So one problem that Maurice worked on, he generalized this problem. Instead of just two participants, he generalized it to a general graph, actually, of multiple participants, and developed a very nice formula for figuring out the deltas. Basically, the intuition behind the delta, or the delay that needs to be added, is that once Alice reveals her secret, we must give enough time for the secret to be added to the blockchain, propagated through the network. Bob can see it and go back. If you remember basic things about blockchain, Bitcoin especially, it takes about an hour to commit a transaction. It takes, for every 10 minutes a block is generated. You need to often wait 6 minutes for it to come back, to be committed, meaning to be deep enough. So we have to wait a little. So as a result, there is an interaction between the different protocols, between the different interactions between Bob and Alice, so that you need 4 deltas for Alice and 2 deltas for Bob. If the time is 12 hours, then we know that this is going to result in the formulas that they had. Okay, so this was the situation basically that was developed by Nolan and generalized by Maurice. So there's a question about fees. Fees are going to be, so this is orthogonal to the underlying system of how fees or gas is going to be developed. But we assume that whoever is putting and getting rewards is going to get the fees. So is going to have to pay the fees. So Alice will pay her fees, Bob will pay her fees. Everybody is interacting with their blockchain and reacting to it. But let me come to a problem that we face in databases, which is failures. What would happen if Bob was actually under attack? Say this solution is a very synchronous solution, depending on timers. There need to be the synchronization. The notion of this many hours or this many minutes is crucial for the protocol to work. If Alice does a denial of service attack on Bob, so enough time so that Bob doesn't react fast enough during this last delta, then Alice could actually take her money also. So she would get Bob's money and get her money. So what we need is to develop a solution that basically guarantees atomicity. This is an atomicity violation. We've been working on atomicity problems, 2-phase commit, 3-phase commit problems for a long time. Commitment protocols were designed so that if one transaction commits, then every transaction commits. If one of them aborts, all of them are aborted. And so using time locks can lead to an atomicity violation. And what we have done is we have looked into solutions that avoid this problem. In particular, we have proposed, and this will be coming up in the next VLDV, I hope it will happen physically, I don't know, it might be virtual also, which addresses this problem. Concurrently with us, actually, Hurley, Shrira, and Barbara Liskov have developed a quite similar approach, and it's going to appear also in the same VLDB on cross-chain deals. They call it deals instead of transactions. So so let me now go to this idea of how do we solve the problem. So this problem is very similar to atomic commitment. Let me remind you of what a simple atomic commitment protocol, which is our traditional two-phase commit. How does two-phase commit work? Two-phase commit works by having multiple participants, and let's say they want to get married. And what they do is you need to have a third authority, a coordinator, and the coordinator asks them a question. Do you want to get married? What's your vote? If we have multiple transactions, sub-transactions, can you commit these transactions? And if everybody says yes, then they are married. If one of them says no, then there's no marriage. That is the idea. You ask for votes, you get back answers, and then the coordinator collectively knows about what is happening, collects all the answers, and so if everybody says yes, then it's committed. If a single veto comes out, then it's an abort. So that's two-phase commit. Now we want to implement a two-phase commit-like protocol, but in an environment where I'm dealing with blockchains and malicious behavior. So what we're going to do is we're going to have, remember the context, I have 2 or 3 or 4 multiple blockchains that are trying to do a transaction across all of them. In Alice and Bob, it's between Ethereum and Ether and Bitcoin, and they want to do the transaction between the 2 of them. So what we're going to do is we're going to add another blockchain. It could be one of the other ones, or it could be different. It doesn't matter. But we are going to add another blockchain that we are going to call the witness blockchain. And the witness blockchain is going to act as the coordinator of the 2-phase, 3-phase commit protocols, but in a malicious environment. It is going to be a blockchain type of solution. So once a decision is made, all the transactions in the swap must follow the decision. Either all of them are committed or none of them are committed, irrespective of whether failures happen or not.
So just a quick clarification.
So the problem is, how does an outside blockchain, a third blockchain, so we have 2 blockchains, let's say in our example, and there's a third one that needs to maintain and verify that Alice did put her X1 transactions into her blockchain, that Bob actually put his Y ethers into his blockchain. So there are 2 transactions that are on 2 different blockchains, and some outside entity needs to verify this. Now, what this third entity, the blockchain, this witness blockchain, can do is to maintain an entire copy of the blockchain. But that would be an overkill, because we would really require everybody to have a copy of all of the different blockchains. So instead, what we're going to do is we are going to try and solve this problem by having each of the blockchain providing evidence that it has that transaction. And that's where the interaction between the different blockchains is going to happen. So I need to be able to do cross-chain validation and verification that there is a particular event, there's a particular block that is available in one of the blockchains. So this is, I'm introducing the problem to solve this particular problem, but I believe that this idea of cross-chain verification can be useful in other contexts in the future. So let me give you a very simple and naive approach of how to do this thing. Let's assume that blockchains do not fork. There are no forks. So it's always, I'm just guaranteeing that it's a linear long list. There's a current head, and we need to verify that in the verified blockchain, there's going to be a transaction T1 that implies that Alice has put her money into that blockchain. So and we need to know that the transaction was put after the current context. It doesn't matter if it happened before. So we need to have an anchor or a current head that will tell us where we started from. And that is going to be passed over to the verifier. So we have the verifier who you can think of it as my witness that I want to eventually have. And what he's going to do is we're going to have a copy of that blockchain. So we know that header. And then once Alice puts her transaction, for example, of interest, then what the verified blockchain does is it takes this linked list, which can be here, you could have more than one block in the middle. And this is the evidence. This is the evidence that I have in my blockchain a transaction T1 that occurred after a particular point in time, which is the current head. This is the evidence that TX1, transaction 1, is in the blockchain. And then this is sent over to the verifier, and the verifier now looks at this evidence and determines that, yes, it satisfies the conditions. How does it do the verification? So this is in the context of, if you remember with blockchains, we have to validate things. So here we're going to verify not the transactions, but this particular context. So each header includes the hash of the previous header. So the verified blockchain did not lie about anything. The proof of work of each header is correct. There's a lot of work that has to be done. TX1 does contain the money that Alice actually puts. And this is the evidence that ensures that the transaction is actually in the blockchain. And it's sufficient if the verified blockchain has finality. What do I mean by finality? That the mined block is there for good. But I know that in real blockchains, we can have forks. So I cannot just rely on this naive approach of taking current point and looking after it, because what if there is a fork and the bad guys actually maliciously started an alternative branch of the blockchain? So what if forks happen? So what I'm going to do now is to generalize what I said before so that I can include the possibility that there is a fork. How does blockchain, permissionless blockchains, Bitcoin in particular, get around the problem? By saying that it is deep enough that my block that I'm interested in has been mined and there's a long enough number of blocks after it so that the probability of it being forked out is very unlikely. So we need to verify that TX1 is actually in the verified. So instead of just taking the current head, I need to take a current head and know that it is deep enough so that the current head is not going to be forked away. It's not going to. So let's say D blocks. I send this information down to the verifier, and then I wait for my transaction to happen. Then I wait for it to be D deep so that I don't get into trouble again if it's. And now this is the evidence. So the evidence is actually a longer chain. It is the original point that is D deep, and then the transaction that is also D deep. This is sent over as the evidence to the verifier blockchain. And now we repeat the same process, and each header needs you verify that the headers and the proof of work and everything is the transaction, and that everything is D deep. Obviously, the cost of generating evidence depends on the D. The D plays a critical role. So in the paper, you can look at this later on, we actually play around with, delve more into the idea that the depth should be a function of the value of the transaction. And if the depth is deep enough to if the chance of forking, if the resources needed to fork the system is bigger than the worth of the transaction, it's not worth doing it. So we play around with this. So now we have a building block of how to do verification across different blockchains. To solve our original problem of atomic swap, what we do is, as I said before, we're going to have a witness blockchain, and the witness blockchain has to collect all the information from the various different participants. In particular, in our example, we could say Alice and Bob. So it needs evidence from Alice's blockchain and from Bob's blockchain. It collects those, verifies that all of them are correct, have all put the actual amounts that they are promising into their corresponding blockchains, decides to commit the transaction. And once that decision is made, that information is stamped into the blockchain and it's going to be committed. Now, each of the assets blockchains need to verify from the blockchain that it has been committed. If it's aborted, it can also abort. So we need this actual module of verification in both directions. For the network, for the witness network to verify the different blockchains, and then for the different blockchains to verify that the witness network has committed. So the details, there are a lot more details, and I'm going to leave you till you can look up the details or wait for us till we are in Tokyo, I hope virtually or in real life. I'm going to now switch to permissioned blockchains. If there are any questions about the permissionless, if you want to put something in the chat box, now would be a good point in the middle.
So just a clarification. So this must be a totally separate blockchain, right? The third one. Hello, can you hear me?
So if there are no questions, I will continue and then I'll take questions in the normal way at the very end.
Can you guys hear me? I'm trying to ask a question.
So
can you hear the question? Professor?
Now let's go to the permissioned world. So if you recall, in a blockchain, we need consensus. And in Bitcoin, it was solved. I can hear the question. Oh, there's a question. Sorry. Can you repeat the question?
Can you hear me? This is Murat.
Hi.
Can you hear me?
Yes, I can hear you now. Sorry.
That's okay. I was trying to ask. So one clarification I want to have is that, so you have to have this third separate blockchain. You cannot use one of the blockchains with a different smart contract or something. It has to
no, the answer is I can actually use one of the other contracts, one of the other blockchains. So it is very possible. It's easier to conceptually think of it as separately. But
okay, so you don't need to really have a third one.
So it works.
Third
yes.
contract.
No, I don't need a third one. It just needs to be one of them. It's a coordinator-based approach. And as you know, there are coordinator-based and decentralized approaches. We are taking the coordinator-based approach here.
Okay.
But it can be any one of the participants. So it doesn't have to be a specifically extra one. Actually, we have an implementation now that uses one of the two.
Okay. Thank you. There's another question on the chat. Please look at it.
Have you considered forward recovery? So what we are doing, we have not yet, as you see, this is just work that we are working on. So there are a lot of very interesting problems. At the moment, we are assuming that we are working in an environment where if all of them say yes, it's going to be committed. If one of them says no, it's going to be aborted. So it's backward recovery. Forward recovery would require us to persist and continue trying again and again. And we're still not, no, we haven't worked on that yet. That's a very good question. Thank you.
Mm-hmm. Yeah, I also got a question. So what about the conflicts between transactions? So suppose we have transactions.
Yes.
And then we have
So yes, there could be conflicts between transactions. At the moment, the way I described it was very simple. So there are no conflicts because Alice is using her money and Bob is using his money. But in general, what you can do is during the verification process, then you can validate that there are no conflicts. You can actually even detect if there's a cycle. I will get more into this type of conflict and detection in the permissioned world where we have pushed it further.
Okay.
These are all very good questions. So what you're seeing is, and I'm happy that these questions are coming up because they indicate that a lot of our database background is really helping us to identify problems that we have the tools to solve. We know how to do recovery. We have write-ahead logs. We know about conflict graphs. We know about dependency graphs, etc. So I think we really have a lot of tools that have not been incorporated into this world. And if we're going to use blockchains in this type of environment, everyday environment that really deals with regular transactions, and to be fair, there is already existing a lot of work that addresses many of these problems. But it is interesting that we have all these tools and techniques that are going to be very helpful in this context. Okay, good questions.
Thank you.
Okay, so if there are no more questions, I'll take off my earphones and switch back to the presentation. It's just easier when I don't do this. Okay. So in a permissioned world, it's the same consensus problem, but now I know the number of participants. It's just that we don't necessarily trust each other. So in this context, and this is what happens in a permissioned world, and as many of you are familiar, this is common in supply chain systems, etc., where lots of different entities, enterprises, participants want to work with each other on a flow, on something, but they do not necessarily trust each other. In this context, what permissioned blockchains have done is to use standard distributed consensus protocols, and in particular, PBFT, practical Byzantine fault tolerance, has been used widely. So this is an old problem that has been around and has often been used in the context of state machine replication. I replicate objects, my data on multiple machines. When an update takes place, you update the different copies, you run consensus, you run a replica control protocol, and then you answer back. And now if a failure takes place, you have other copies that you can deal with. Traditionally, in databases, we've looked at crash failures, and a protocol that has been developed in to solve this problem in a crash environment, and that has widely been used even in Google, like in Chubby or in Spanner, is the consensus protocol Paxos due to Lamport. And here we have a bunch of generals, and they want to all agree on either to attack or to retreat. It's again a coordinator-based approach, and you end up agreeing on a certain decision. Abstractly, you have a leader election, you have a bunch of protocols, you have a bunch of participants, processes, you elect a leader, and then you make sure that the value that the leader wants, whether it's commit, abort, attack, retreat, etc., is made fault tolerant. So you typically try and get a majority to agree on the value that you want. And once that value has been made fault tolerant, meaning there are enough sites that are aware of it, you announce the decision. We've been working on this in an orthogonal thread where we are connecting many of the ideas in distributed systems, for example, Paxos protocol and others, with database protocols, for example, two-phase commit and three-phase commit. And I refer you to our VLDB paper last year. Now we are in a world where we could have malicious failures. So luckily we have a very nice other protocol, PBFT, which assumes that the underlying infrastructure is not trustworthy. And in this case, we are going to, instead of just having the fault tolerance send it out, the primary could be malicious. And as a result, what is done in that protocol is you end up adding an extra phase, a validation phase that can be added to the process. As you'll see that with PBFT, we have, in comparison to the crash failure, we have one extra phase, so think more latency. And so we add an extra phase because the primary could lie, so we need an extra validation, but there's also a lot more communications. It's n square instead of n. So there's an explosion in terms of number of messages as well as the phases. So think of latency and throughput. If you are interested in more about this, we have a tutorial on Wednesday in ICDE where we will delve more into consensus and its relation, and the various solutions and its relationship to databases and commitment protocols. So I'm going to be using this during the rest of the talk to kind of tweak out certain things. So within permission blockchains, one can look at various aspects or dimensions that are troublesome. One of them is how to make them perform better, how to scale better, how to provide confidentiality and verifiability. I'm not going to have time to discuss all of these problems, but I'm going to try and tweak it and give you some notion of how we have been working on addressing these things. Let me start with the problem of blockchain performance. So if you recall, in a database context, and again, I put this meme to kind of indicate I'm talking about databases, as was alluded to in one of the questions, Jiang Lang, I think, was that we have looked at concurrency control. In particular, we have different approaches to deal with concurrency. We have dealt with when there are conflicts between transactions, we have a pessimistic approach or an optimistic approach. In the pessimistic approach, we typically lock the objects that I want before I do anything. What does that mean? In the context of what we're talking about, it means I establish the order, the serialization order, before I execute the transactions. So I decide on the order. Once I've decided on the order, then I can execute, and I know that I'm safe. Alternatively, we have optimistic concurrency control, where we execute the transactions first, optimistically assumes that there aren't any conflicts, execute them first, and then at the very end, verify. Look for right-read conflicts, look at dependency graphs and figure out serialization graphs and figure out if there was a conflict or not. And if there was a conflict, I might have to roll back, abort, etc. So this is from a database world. Let me look at Bitcoin just for a little bit. I know it's permissionless and I'm talking about permission, but let's look at Bitcoin and think about it in this mode of thinking, of execution. We have a client and I have a whole bunch of processes that have blockchains, and a client wants to do a transaction. It broadcasts it to all the possible miners that are around. They are going to validate the transaction is correct, meaning I validate that this guy really has the assets that they claim they do. And then you do the mining, the solving of the puzzle, the proof of stake, whatever the protocol is going to be. Once the order is done, and it's important here to say that the order, the whole mining process is trying to figure out a leader, one of them that is going to win. In a way, it is deciding on the serialization order. It's deciding where in the blockchain the next set of the next block is going to be put in. Once that has been done, once I've established that I am the leader, I've solved the puzzle, I'm going to add the new block to the blockchain. Remember the picture? I'm going to add to the head of the linked list. Then I broadcast the block. The block has the transactions that are going to be executed, and they are executed at the very end and appended to the different copies of the blockchain. So in a way, Bitcoin is pessimistic in this sense. It's taking the pessimistic approach. You basically don't know the number of participants, so what do? We end up using mining, and you end up adding a block. Obviously, I was not getting into the problems of forks. Well, this is a problem that we know, and some of the questions alluded to. When I have a fork, Bitcoin has a decision of what happens if the serialization order is not correct. So they follow the longest chain, and critically, a bunch of transactions are eliminated or aborted. So, and they have to be resubmitted or something. This is really very similar to what we talk about in a database context. So some of the early works on blockchain in a permissioned world basically took this model of Bitcoin and translated it directly into the blockchain world. So Tendermint is an example where you have a set of nodes, and I'm just taking examples. There are lots of other examples. And basically they order the transactions. So they are doing the pessimistic ordering early on. It executes a Byzantine fault tolerance protocol and agrees on what is the next block. Once that is done, it is executed and appended to the blockchain or the ledger. What happens here is we don't have much concurrency. We are really executing everything in order because this is what the blockchain does, is it has this linear order that is being preserved. So an optimistic approach was proposed by, for example, by Hyperledger Fabric, and in it, they use the terminology execute, order, validate. So it's execute first, which is the optimistic approach. So you execute the transactions, you have a set of nodes that are going to execute the transactions, then you order, so there is an execution, then you order them, and finally you validate that everything is correct and you add it to the blockchain. So they have different types of nodes, they have clients, they have endorsers, they have orderers, and for the purposes of my talk here, I'm focusing on the orderers. They establish the order among the different transactions using a concurrency control protocol. Actually, their consensus protocol is pluggable. They can use a Paxos-like if they assume that the participants are crash, or they can use a PBFT if they assume that the participants are malicious. And so you have different trade-offs, 3f+1, 2f+1. And the problem is now, when we come to the end, to the validation, if transactions are conflicting, then they need to be aborted, which is not surprising. This is what happens in an optimistic approach. So if there's high contention, there could be weaker performance. But if there is low contention, which some would argue is the common case, then there will be good performance. Now, let us delve into this issue. How do we solve that problem? So we have been taking an idea that is available from the database world, which we've talked about, which is dependency graphs, which captures basically conflicts between transactions and gives us a partial order. So what we've done is we've proposed an alternative approach, par blockchain, which is more pessimistic. So it's going to go back to the idea of ordering first and then executing, but it's going to try and exploit the dependency graph to allow parallelism. So I will take a conservative approach, order first, so as to support high contention systems, but once I've executed it, I can figure out where there is potential for parallelism or concurrency and exploit that during the execution. So you order first, and while you are ordering, you generate a dependency graph. A dependency graph that captures the dependency between the different transactions. Then I execute, and I execute based on the dependency graph that was given. So now I know that I can execute everything in a consistent serializable way, even though they are going to be executed in parallel. Obviously, since I'm doing the execution first, if I have non-determinism, I will not be able to recognize this, adapt to this. So what we do, but we can recognize it. So if there is non-determinism in the execution, it is detected and resubmitted. So what you'll see is there's a trade-off between the two different approaches, the optimistic of Fabric versus par block that we are proposing here. One of them is optimistic, one of them is pessimistic. One of them does better when there's high contention, one of them does better when there's non-determinism. There's another idea that I want to touch on, which is scalability. So typically in a database world, if I have a lot, if my data is too large, if I have too much throughput that I need, if there are storage or latency issues, what we do is we typically shard the data across different machines so that I can exploit the different servers to give me better performance. So what can be done in a blockchain environment is, again, you can actually scale by having multiple blockchains that will shard the data that you are dealing with. And we've been working on such a solution. There are various approaches. I think I'm running. Can you give me how much time I have left? If you can write it in the chat box, that would be good. So sharding is an approach that has been typically used in a database context very successfully to ensure good performance. What we've been exploring is trying to exploit sharding in an environment where I will still use consensus protocols. Now, consensus protocols, especially PBFT, requires that the number of processes in the system be greater than or equal to 3f plus 1, where f is the number of faulty processes. Now, typically, I would say that there are a lot more in any given system. N is much bigger than 3f plus 1. So what we are proposing is to guarantee safety, we are going to create we are going to break our N into clusters where each cluster has 3f plus 1. So within each cluster, I know that I can run PBFT consistently and guarantee safety. And exploit this across different clusters. So I have the data is going to be sharded across different clusters. Within each cluster, you're going to have a blockchain that is going to be replicated on 3f plus 1 and is going to execute basically PBFT on it. But processing in the different clusters can be done in parallel, and hence I get better performance due to the parallelism. So the data is sharded. Obviously, the challenge that we all face whenever I have a sharding situation is that I need to have cross-shard transactions. If all the transactions were executing within one shard, this would be great, but often we typically don't. So we have to address this problem. And so we have a proposal called Sharper, and in it, we expand the idea of a blockchain instead of being a linear list as is typically done. And by the way, this idea has also been around in the blockchain literature. I think of it as a DAG, but the DAG is not maintained by any particular node. Instead, every node or every cluster is going to have its view of the chain. So all the local transactions and any cross-shard transactions are going to be stored on the particular cluster that is in charge of that node. So here you end up with lots of good opportunities for parallelism. We've explored various intra-shard consensus as well as cross-shard consensus protocols that give us different alternatives. I'm going to, I think, given sharding ends up being actually quite useful in the context of privacy and confidentiality, because if I can break the data so that my private data is only with me and not visible to the others, I can only share what is needed to be shared only when there is a cross-shard transaction. So we had a paper in last year's VLDB where we basically proposed a caper that exploited sharding to help address problems in the context of this multi-blockchain sharded data that has confidentiality. Again, it uses a very similar idea to what I described before, and each site maintains its own view, and hence I am in control of my data and I can only make visible what I want to be. And that's why sharding and confidentiality kind of play a strong role with each other. So I have 1 or 2 minutes, so I want to give you a glimpse of some very recent work that we've been doing, which is actually going in the opposite direction, trying to exploit ideas from blockchain world and taking it to the database world. So databases have traditionally assumed that the underlying structure is trusted, and that's why we used crash, etc. And here are various examples that illustrate that there are serious concerns about this. Now, in a normal trusted world, I execute my transactions and I assume the infrastructure can only fail. I'm going to stop in 1 minute, so don't worry. So the question is how to guarantee correct execution in an environment where there are malicious failures. So typically we use replication. Replication, if I have a crash environment, requires, if I want to tolerate F, I require 2F+1 to tolerate F failures. But if I have malicious failures, I need 3F+1. So if I'm starting with 2 nodes, to tolerate that, I need 7 nodes. That's a lot. In fact, it's not only a lot, but knowing how many failures can happen is a good, challenging problem in its own right, and from a practical point of view, might not be very practical. An alternative approach is to use fault detection. And in this case, you allow failures to happen and then detect the faults and undeniably link the failures to the non-trustworthy server. This has been used in reliable distributed systems in the past few years, actually a while back, peer review and CATS. And in those cases, you add an auditor and the auditor goes and checks what is happening. So it's critical to have enough good information for the auditor to figure out what has happened, and then the threat of auditing prevents people from acting badly. And the nice thing here is instead of requiring 3F or 3F+1 to tolerate F failures, we can actually tolerate as many failures as we want, as long as I have more sites than I have faulty processes. So here is where we are proposing to use a blockchain. So here is the basic database context. You have transaction processing, commitment, and the data store, but we are going to add a tamper-proof log that is reminiscent of blockchains to give me an idea of everything that has been happening. And in particular, we are going to use a blockchain that uses cryptographic hashing, so hash pointers. It also uses collective signatures, so ideas that are coming from the cryptography world to ensure that the transactions are all executed together. This is a very recent result that we're going to have in ICDCS, distributed systems, and we are proposing FIDES, which is a full-fledged database system, database management system that that can live in an untrusted world. The cryptographic techniques guarantee the asset properties. In particular, we've delved particularly into the commitment problem in an untrusted world, and that has not been explored before, and we are quite excited about this. So I'm coming to the end of my talk. There's a lot we can learn from database technology that can be useful in a blockchain world, and as I alluded to at the very end, from the blockchain world, there are ideas. Having this blockchain that cannot be tampered with is a very strong tool. Blockchains can have made us as a database community very aware that malicious failures are challenging. We were focused on crash failures, and I think this move has been a very good move. Permissionless world blockchains are full of very interesting opportunities. They open a world where we do not know the number of participants, and hence there are deep intellectual challenges that have to be dealt with. It's an asynchronous system. And this is why, if you go back to the first part of my talk, there were really interesting challenges that require deep thinking. For the permissioned world, I think there are lots of opportunities for using ideas that are in distributed data systems into the database world. So it goes all ways. I think there's a lot of very interesting problems in the entire space. So thank you, and I'm ready for questions.
Yes, thank you. Thank you for this very informative talk. There's one question remaining in the chat box from Professor Pei Jian regarding the first part of permissionless scenarios. So the question is about,
I can read it. What if Alice's answer is kidnapped by Ada's answer is kidnapped by Carl, and Carl gets okay, so that will not happen because Alice has put in the smart contract that the money goes to Bob. So the secret is visible to everybody. Actually, the way I explained it was that Bob will need to answer, will need to pick it up and put it in the other blockchain. But it could be anybody can do this. But the whole protocol itself guarantees that it's going to be reflected. It goes to Bob. So that's part of the smart contract itself. In Fidesz, will it be expensive for blockchain to audit? Yes, it will be expensive. So auditing is an expensive thing, and you're right. So I think I'm working with the assumption, at least for now, and these are really very recent things. So there are lots of interesting questions that we are asking ourselves. But in my point of view, the benefit of auditing is that it prevents bad behavior. Hopefully, we will not have to do auditing too many times. I do not go out and steal. Why don't I go out and steal or raid a bank? Because I'm afraid of being caught. If it was easy, I could have done it if I knew that there was no penalty. So the fear of doing this, I hope, will prevent it. However, we have to make sure that we have the system. That's why we have a legal system. We have juries. It takes a lot of effort. So auditing, at the moment at least, I'm thinking the auditing could be probably done by lighter nodes, but we are still working on that. So that's a very good question. All these questions are very good.
yeah. So because we are running out of time, so we may take one more question, if any. You may just unmute. If questions, you just can unmute yourself, then you can speak up.
Yeah, I can hear now. I'd forgotten my earplugs. I can also put my mask if you want, so that I'm completely ready. Okay, thank you.
Yeah, thank you, thank you. Thank you again.
It's challenging to give an online talk. I like to get the feedback of the audience, so it's good to hear any positive comments or anything, because
yeah, also a lot of questions generated during your talk. It's very interesting.
Thank you very much. I really enjoyed it. Good luck, and see you around. I hope to see you all somewhere soon, in person.
Yeah, thank you again, and also thanks for the audience.
Thank you. Goodbye.
Bye-bye. So let's have a short break of 5 minutes, then we'll resume the technical PEP sessions in 5 minutes.
The speaker is approaching the judgment towards fair proof of blockchains. So the speaker is really kind of this from computer technology. That's welcome.
Hello, everyone. Can you hear me?
Yes, yes.
I'm Ci Jing from East China Normal University. I'm also the co-chair of this workshop, and I will chair this technical session. In this session, we have 4 papers, and the first paper is titled Block Interval Adjustment Toward Fair Proof of Work Blockchains. This work comes from Tokyo Institute of Technology. The author is Ricky Kanda. Let's welcome.
Hi. Can you hear me?
Yes.
Thank you.
So do you want to play the video?
Okay.
Anshu, can you play the video?
Yes, I'll play the video.
Let me start my presentation. I'd like to talk thema like this. First of all, I'll talk about the background of proof of work blockchains. Blockchain is a mechanism to distribute and manage transaction records among participants on a peer-to-peer network. Participants on a peer-to-peer network say blocks to link them. We refer to a block as combining transactions. On the other hand, what is the proof of work, that is POW? Participants on a blockchain network repeat the hash calculation until they find a value that satisfies a condition. Participants who find the nonce get the right to create a block. They call a miner. Such a system is called POW. Bitcoin or Ethereum are famous as a POW blockchain. Next, I'll confirm the process of updating the ledger, which is managed on blockchain. A user issues a transaction and broadcasts it on the nodes. Node means participants on a blockchain network, and a miner who has solved a hash value creates a block and broadcasts it on the nodes. Finally, a node receives the block and appends it or its local ledger. This completes the update the ledger. Next, I'll introduce issues pointed out in the existing research about block interval and fairness. Block interval until a block is generated and next block is generated because of the type of blockchains. In point of user's view, user want to shorten block interval because shortening block interval enables to be shorter latency or higher TPS. The TPS means the transaction per second. On the other hand, in point of miner's view, miners become unfair if block interval is too short. Let us assume the next situation. If block interval is 15 seconds, but block propagation delay is 14 seconds, mining time is only 1 second. This is an unfair situation among participants because block propagation delay differs by each node. To prevent such an unfair situation, Klman et al. Processes fairness to define a lower bound of block interval. 90% propagation delay means time until a block delivers 90% nodes of network. And block interval of POW blockchain is basically fixed. I think it's a problem because the lower bound of block interval changes by block propagation delay. So it should be balanced between performance such as TPS or latency and fairness. Next, let's confirm a goal of our research. First, we calculate the lower bound of block interval by proposal fairness. And I'll compare our proposed fairness and existing fairness. Second, we propose block interval adjustment method and confirm it works well on the simulator. We did two major experiments. One is the confirm block interval adjustment when changing propagation delay. The other is to confirm the ratio of fair nodes increased by adjusting block interval. What is the fairness on a POW blockchain? Our proposed fairness is based on an X idea. The mining success rate of miners depends only on computational power. Hash rate means the number of computing hashing functions per second. The rate of nodes, the difference between the hash rate and the effective hash rate, is within the alliance error. Distribution of effective hash rate equals nearly when blockchain is too long. On the other hand, increasing research refers to fairness as most participants have sufficient time to participate in the competition. We need to calculate effective hash rate to calculate our proposed fairness. To understand the idea of effective hash rate, let's think about such situations. This figure shows four nodes of blockchain network. The block interval is set 1 minute, hash rate is set the same power. It takes 30 seconds to read the nodes on the right side. If the node on the left side is standard about block relay delay, the node on the right side expends 30 seconds to create a block, which means the nodes have just half of time compared to the nodes on the left side. Generalizing such an idea leads to such a formulation. What I have ever said is the case of one block relay. Next, we saw the distribution of effective hash rate in the case of block relay on many times. We calculate the cumulative effective hash rate and the takes ratio to the effective hash rate of the entire node. Next, we will give you a definition of proposed fairness. Fairness is a ratio x of the number of nodes where the difference between the mining success rate and the hash rate is within the allowable range. A mining success rate corresponds to the effective hash rate for a sufficiently long blockchain. This formula shows how to calculate fairness, and delta is the reliable range. Its epsilon satisfies the stochastic inequality, and epsilon is 0.01. From the central limit theorem, the stochastic inequality follows a normal distribution, which means an acceptable mining success rate with a probability 0.01. Next, I'll talk about experiment preparation to calculate fairness. Summing up how to calculate fairness, we need a block propagation delay distribution to calculate effective hash rate, and need effective hash rate to calculate fairness. We used the survey of Bitcoin network and calculated it when the ratio of fair nodes exceeds 90%. We estimated f of t, which follows the gamma distribution by maximum likelihood estimation. This shows the result of the fairness experiment. Horizontal axis means block interval. The scale 1 means block interval 5 seconds. The scale 4 means block interval is 20 seconds, because 90% block preparation delay is about 5 seconds. We need to know how long block interval should be when fair node exceeds 90%. According to this figure, when block interval is from 10 seconds to 15 seconds, we learn that the ratio of fair nodes exceeds 90%. And we can compare our proposed fairness to existing one according to this figure. If block interval is approaching to the lower bound block interval of existing fairness, we learn that the ratio of unfair nodes is increasing too much. This is the first half. Next, I'll talk about the proposal of block interval adjustment. Block intervals should be adjusted while satisfying fairness, but participants on blockchain network cannot know how much fair they are now. Then how do they know how much fair they are? The answer is sharing fork rate, because both fairness and fork rate depend on block interval and propagation delay. It has pointed out by the existing research, fork rate depends on block interval and propagation delay. Next, I'll explain you about fork rate. In a pure double blockchain, basically miners create only one block of the same height, but sometimes make multiple blocks of the same height. They call such a thing fork. But in the end, a blockchain is converged to only one history. So they call the right history main chain, and call exclusive main chain orphan blocks. Then we can define fork rate as the number of orphan blocks by the number of blocks of main chain. Next, I'll show you how to adjust block interval. The basic idea is to adjust block interval to keep fork rate constant. The formal definition is such a formulation. For example, when the fork rate doubles, the block interval doubles, and when the fork rate decreases by half, the block interval decreases by half. This is the purpose to give fairness, that is fork rate. The relation between fork rate and block interval is as it is shown This formulation has been imported in the existing slides. Next, I'll confirm that block interval adjustment works well on a simulator with the two major experiments. One is to confirm block interval adjustment when changing block propagation delay. In the experiment, we have three scenarios. Each scenario differs from how propagation delay change. The other is to confirm the ratio of fair nodes increases by adjusting block interval adjustment. Next, I confirm the settings. Settings on a simulator is as follows. Settings on block interval adjustment is target fork rate is set to 5%. This is sufficient fair. And how to calculation this value is omitted for the sake of time, sorry. The experimental results of the scenarios on this slide. In scenario 1, the fork rate is nearly 5% from 16,000 block height because this is block interval adjustment is run every 8,000 blocks. In scenario 2, fork rate is away from 5% fork rate because this is propagation delay is decreasing radically in the upgrade interval. In scenario 3, the fork rate is nearly 5% from 16,000 block height, but in case of constant block interval, fork rate is approaching to 5% because the propagation delay is decreasing. In both scenario 2 and 3, the results show fork rate is approaching in case of adjusting block interval nearer than in case of constant block interval. Next, I'll confirm effects on fairness. When utilizing block interval adjustment, the scenario in the experiment is as follows. It is 800 nodes and block height of 80,000, 0.7 times the bandwidth and the target fork rate of 5% every 1600 blocks. And the figure on the right side shows the changes of fork rate in case of adjusting block interval, and note that is the ratio of pair nodes is 85%. Without proposed technique, the ratio of pair nodes is 98% with it. Next, I'll give you discussions about block interval adjustment. In terms of practical applicability, sharing fork rate is achieved by simple modification of block relay protocol. Then we can expect the scenario of constant bandwidth is the closest to the current situation of Bitcoin. Finally, this is completed after I show you conclusions. One is by proposing final fairness, the lower bound of the block interval could be stricter, so 90% fairness is achieved when the block interval is from 2 to 3 times the block propagation delay. The other is to propose the block interval adjustment method, and we confirmed it works well on a simulator. That's all, thank you. Thank you.
Thank you. And anyone has a question? And I see Jiliang has a question. How did you define fair nodes in the experiments?
All right. In this experiment, so the difference effective hash rate and the hash rate the fair nodes is defined by the differences between effective hash rate and the hash rate.
Okay, and any other question? Okay, thank you. And we will move to the next paper.
Thank you. Thank you so much.
The next paper is towards identical blockchain systems with enhanced provenance, given by Shlomi Linoy.
Yes, hello.
Yes.
Should I share my screen?
And maybe help to play the video.
Okay. Hello, my name is Shlomi Linoy, and I'm going to discuss the paper that I wrote with my colleagues called Toward Eidetic Blockchain Systems with Enhanced Provenance. We'll start with the motivation. So the adoption of blockchain technologies that use smart contracts is rapidly expanding in the industry as well as in the academia. In the industry, the smart contracts are mainly used to manage cryptocurrencies, securities, real estate, valuable tangible assets, with a projected market size of more than $4 billion in 2020 and more than $162 billion in 2027. A little bit about smart contracts. So smart contracts are programs that operate on the blockchain's current global state and produce a new global state. And each smart contract can be executed by a client, another smart contract, or can periodically run using a scheduler. With the increase in size and complexity, there is also an increase in bugs, exploit potential, regulation requirements, and understandability, which can result in impactful financial repercussions. Existing blockchain-based provenance solutions do not facilitate, for example, identifying the root causes of anomalies, investigating malicious actors, or enabling efficient audit tracking for regulation purposes. To enable or to support all these requirements, we would like to know what initiated a state change at a specific time, and how a state was changed at a specific time. So we talked about motivation. We're next going to talk about related work, followed by our proposed system. And then we're going to talk about a use case to give a more detailed example of how our proposed system works. So blockchain has an intrinsic hash chain structure that can inherently track its ordered blocks, the ordered transactions in each block, and the current state of the blockchain. This means that if we would like to analyze historic states of the blockchain, we would need to execute all the blocks and transactions that led to that specific state in order to know what that state was in the past. All these calculations can be very time and resources expensive. So to save a little bit of these computations, Ran et al. Proposed a system that collects the change values of each blockchain state after each transaction, stores it in a Merkle tree with an efficient index, and enables contracts to access this information in real time, which can increase their applicability. But analyzing contracts execution flow requires additional data. Devexeri proposes an eidetic software system that remembers all operations, all the function calls, and all the states at any time. This historic information facilitates querying, for example, what states or calls affected other states or calls, and conversely, what states or calls were affected by other states or calls. So our proposed system is inspired by Devexeri et al.'s work, and we propose an eidetic blockchain system. This system can collect and manage state data of blockchain states, and execution flow, a call graph of contract calls. We do this non-intrusively by modifying the blockchain's smart contract execution infrastructure. So whenever a smart contract is executed, its details is being collected, and whenever some state changes, its details is being collected. So for example, if some state was written into, we collect the state before its data was changed by a specific contract, and after its data was changed by that specific contract. So a little more about the provenance collection. We collect contract calls and their parameters. So the caller, we collect the contract's caller. His name is address. The caller can be a client or a contract, and the contract callee, which can also be a name of or an address of a contract. And the API function and its parameters on the callee contract that was called by the caller. And we store only relevant states, which means that only if a specific state was read or written into, only then we collect that specific state. To manage the provenance, we store the provenance in a database, and we can export it into a graph database to enable visualizing and querying the provenance. We generate two types of provenance graphs. One type is a contracts call graph. Whenever one contract calls another smart contract, we represent this by a node for each smart contract. So for example, we have two nodes, one the caller smart contract and an edge to the callee smart contract. And we can know exactly which smart contracts were executed and by who. And the second type is contracts parameters and state change graph, which for each smart contract call, we know what was the state before that smart contract was called and after that smart contract was called. We continue with the use case. Let's say that Alice would like to get the best deal on a new U phone. She connects to some retail websites, and we continue with the sequence diagram to see how she interacts with this website. So first she would like to see the best offers. So she issues a supplier's request to the sales department for some specific product ID. The sales department propagates it to the supplier's department, and they send the supplier and the price for that specific product ID that was requested and return it to Alice. Alice then looks at the information she receives, and she can see, for example, that supplier with ID number 2 has the best price for the same product that she was looking for. Alice would like to purchase this product with this specific deal, and she issues an order request that includes the product ID and the supplier ID, and issue it to the sales department. The sales department then propagates it to the supplier's department, and the supplier's department issue a shipping request with the client's details to the shipping department. The shipping department then returns the shipment ID to the suppliers, which return to the sales, which return to Alice, and eventually ship the product. Once the product is shipped, the shipping department sends the shipping confirmation to the suppliers department, which sends it to the sales department. Then, in our example, the system then processes the payment. Alice can provide her payment at this point or beforehand. The sales department then pays the suppliers department and send them the payment confirmation ID. The suppliers then pay the shipping department and send them the payment confirmation ID. So how do we represent this specific department on our blockchain? So each department is represented by a smart contract. We have a smart contract, for example, for sales, for suppliers, or for shipping. And each smart contract has its own API functions. For example, for the sales department, we have a specific API function for this to request suppliers. We have a specific API function for order requests, and so on. Each sales department has its own blockchain client to interact with the blockchain and send and get data from the blockchain. Whenever any smart contract is executed, its provenance data is being collected into a provenance database and can then be converted to a Neo4j representation. So this is, for example, one graph that our system can generate. It's a contracts call graph. So for example, if you would like to see all the scenarios, if Alice did have a correct process of all the required scenarios. So for example, we can see that all the scenarios were generated for Alice's specific session. And we can look, for example, in the order request scenario, we can see that the client of the sales department did issue an order request to the sales smart contract, which issued the order request to the supplier's smart contract, which issues the shipping request to the shipping smart contract. If we would like to see, for example, the state inside the supplier's smart contract, we can look at the contract's parameters and state change graph. We can see that the supplier's smart contract node is represented by this node. And it has the contract API that was called and the date when it was called in, and the parameters that were used in this specific API call. We can also see that we have the states of the blockchain before and after calling this specific smart contract. And we can see that only after calling this specific smart contract, we have a new row for Alice in the supplier's orders database on the blockchain. So let's say that Alice was very satisfied with her purchase. She told Bob. Bob also made the purchase, who told Carol. But Carol got to see only the higher price of the U-phone, $135. He was very disappointed, and he called the customer support to try to understand why. Customer support then looks at the provenance data, and it, for example, let's say that it figured out which product that was Carol was talking about, and you can see that, for example, for a supplier with an ID number 2, the product quantity dropped from 1 to 0, and it can see exactly when, who caused that and why. So, for example, we can see that a specific API function order request on the smart contract that was called from client to sales was actually requested, for example, by client ID 1 or 2, Alice or Bob, and they each requested one quantity. And this can help know exactly why that product quantity was reduced and that product was no longer available. So in conclusion, we discussed there's a rapid adoption of smart contracts applications in managing valuable assets, which leads to increasing application size and complexity. This increase results in an increasing potential for exploitation of a larger amount of coding errors and regulation requirements, which can result in hefty financial consequences. So in this paper, we propose a non-intrusive blockchain provenance collection and analysis system that manages the contract's execution flow and their parameters, and the blockchain states before and after each contract call. We further explore how this information can be queried to facilitate better regulatory, quality, and maintenance management. Thank you.
Okay, thank you. And anyone has a question?
Yes. So regarding the performance, we currently did this to show how we can, what we can collect from the provenance and the idea on what we can understand from it. We used for this experimental approach, we used a database like the Neo4j database, and it did contain its own indexes. We didn't implement our own indexes yet for this paper.
Okay. Any other questions?
Yeah. So I got a question. So interesting technique. From what I understand about Ethereum is that it already provides logging in terms of transaction history and internal core history. So what extra information did you log in your infrastructure in order to achieve, to recover the function core graph, and etc.?
So what we propose here is a non-intrusive system for a general blockchain, not just Ethereum. So I'm not really sure what Ethereum collects, but in our example, we collect all the available data. We collect all the states information that were accessed, and we also collect all the API functions and the specific smart contracts and the order in which they were called. And we provide all this information as a complete picture of how everything was run, so you can see exactly, so you can run queries on exactly what scenarios and what smart contracts were called and when and with what. Does Ethereum provide this? I don't know.
Maybe I misunderstand. A follow-up question is, so can you talk about the sort of engineering part or the implementation part of your work? How did you collect the trace? On which blockchain platform?
So we started with the Hyperledger Sawtooth, and we started to implement a function that collects the states as a library whenever you issue a get or set function on the state. And then we wanted to make the idea broader and non-intrusive, so you will not need to actually implement or use any library. So we wanted to push that collection and write the provenance information automatically. So we moved that to, in Sawtooth, you have a validator node for when each smart contract is executed. It's being sent to the validator, and the validator executes the smart contracts and knows about all the smart contracts that he interacts with. So we actually pushed all this logic to the validator, so you didn't actually need to do anything yourself. And we didn't actually change everything on the Sawtooth itself because it was time consuming and didn't have enough time. So we created a simulator that simulates. So the simulator has the same API functions as provided by Sawtooth, but we just implemented our own validator node that does this automatically for us.
Yeah, thank you.
Okay, still another question given by Sanjay. Can you see?
Yeah.
Will the provenance database be a traditional centralized one or a blockchain by itself?
I guess it depends on what you want to gain. So we just generate this information, so you can store it wherever you need. If you want to achieve, for example, if you want to save this information as part of a blockchain, I guess you can save this information on the blockchain itself to preserve the data, so it will be immutable. But if you would like to gain more, if performance is more important to you and you would like to get a better performance, you can also use this data in a centralized database. So it's we generate the information, and this information can be used in whatever application that you need in performance or otherwise. Thank you.
Okay, thank you.
Thank you very much.
Yeah. Okay, and then we will move to the third paper. The third paper, the title is Blockchain Enhanced Distributed Storage and Sharing of Personal Data Assets, given by Janice Grabis from Riga Technical University, Latvia. Let's welcome.
Good morning. I'm Jānis Grabis from Riga Technical University, Latvia. Right now, I'm very far away from Dallas on a very different time zone. There is an 8 hours difference between Riga and Dallas. And today I will present my presentation on blockchain-enabled distributed storage and sharing of personal data assets. This is my co-work with Vladimir Stankovsky from University of Ljubljana and Robert Zariņš, who is also from Riga Technical University. He's a master's student, and he's actually responsible for doing most of the implementation work in this research. Web technologies allow users to create a lot of different data assets like pictures, videos, and so on. And these can be shared over the internet to create value for their owners as well as for other consumers who find these data assets useful. There are two ways how could we share these data assets. One is a centralized approach and another one is the decentralized approach. And nowadays, quite often, we rely on centralized management of our personal data assets. And unfortunately, in this case, we have limited control over usage of these data assets and what are the sharing options. And also our value creation opportunities are limited and set by a body who provides the centralized management services. The other alternative is to use decentralized management. And in this case, there is no single point of control, and sharing conditions and the way we benefit from sharing our resources completely depends on agreement what we make with other parties involved. Blockchains and smart contracts are two technologies very helpful to enable data and value exchange in the distributed case. However, there are limitations related to quality of service, and in particular, blockchains are not well suited for storing large volumes of personal data, especially when we talk about pictures and videos, and also information processing speed is limited. There is a number of other investigations concerning using blockchains for personal data management. And one of the first works proposing blockchains for personal data management is due to Ziskin back in 2015. Afterwards, a number of researchers have investigated the problem. What are the quality of service limitations when we use blockchains for personal data management? One of the solutions is to provide efficient query languages. However, these are mainly intended for finding cryptocurrency transactions which are relatively small storage-wise. Recently, there have been a number of works very similar to our proposed research, and they suggest that by combining on-chain and off-chain processing, we can preserve some of the benefits provided by using distributed blockchain-based technologies, and we could also address limitations concerning quality of service. Therefore, objective of this research is to elaborate a method for efficient distributed storage and sharing of personal data assets within a community of users. Blockchains are used to control access to distributed personal data assets, and conditions of access are specified in smart contracts. That is well in line with other investigations combining on-chain and off-chain technologies. The additional introduction in our paper is knowledge base, and in the knowledge base we maintain community of users who are willing to exchange information among each other, and also it stores information about data assets available, and it acts as a mediator for efficient querying of distributed personal data to meet high quality of service requirements. We refer to this solution as My Data Experience, and this slide shows the main components of personal data management solution. The central point of this solution is a user who owns his or her personal data assets or resources as they are referred in this picture. These resources are stored in a distributed storage. At the same time, there is a community of friends, and information about the community of friends is stored in the knowledge base, and also resources stored by various users are also indexed in the knowledge base. Users use the knowledge base to find information assets or resources of their interest, and access control is provided by blockchains and smart contracts. If the conditions of the smart contract are fulfilled, then the access is granted to friends to access the resources stored by a user. And there could be a compensation. The user of the assets receives compensation, which could be in various forms. It could be monetary compensation or credits for sharing resources and so on. In order to implement the My Data experience, we have specified a number of data management processes. One is storage of personal data, another one is sharing, and the third one is search of personal assets. These processes are detailed in the paper, and this slide shows the search process. In this case, a user looks up in the knowledge base for assets of her interest, and there could be various criteria for doing search. We could be looking for assets owned by particular users in our community, for particular type of assets or keywords, and so on. If we are interested into the assets, then we can ask for the blockchain, what are the access conditions, and blockchain returns access to these personal information assets. Using this information provided from the blockchain, we request these assets to the distributed storage, and we actually receive the file we are interested in. At the same time, also by executing the smart contract, the asset owner could be compensated by providing the asset. We implemented My Data experience using a set of technologies. First of all, the simple web application is developed using the React framework, and this web application allows to perform all the aforementioned processes. We use Ethereum blockchain, and in particular Ropstein test network, for implementing blockchain functionality. The transactions are handled using Ethereum wallet, as also shown in the slide, and the contracts are implemented using the Solidity programming language. We use interplanetary file system to provide distributed storage facilities. In order to evaluate My Data experience solution, we compare it with on-chain storage of data assets. So in the case of My Data experience, we combine on-chain and off-chain data storage. And here in the experiment, we will compare it with simple on-chain storage of data assets. And we will use two performance measures. One is a storage size, particularly on-chain, and data asset search efficiency. How long does it take to find the necessary data assets? This slide shows the first set of experiments concerning storage size, and we have uploaded 3 files on-chain and using My Data experience. And we can see that if we store our data assets on-chain, then the blockchain size increases very significantly, and that results in a significant gas consumption. On the other hand, if we use My Data experience, then only metadata of the assets are stored in the blockchain, and the size of the blockchain is not dependent on the file size, and the blockchain size increases only gradually. We also compare file search efficiency, and we considered multiple scenarios depending on what conditions are used. So we try to search for files according to their owners. We try to use files according to their type and according to their content. And in the slide, we show what is the execution time for various scenarios, again, using on-chain storage and My Data Experience solution. And we can see that execution time of file search, again, is significantly shorter for the My Data Experience solution. And it is not significantly dependent on a type of search we are conducting. And to conclude, we say that My Data Experience solution is shown to adhere to principles of privacy by design, and it provides users a full control on the way personal data assets are stored and shared in the community of users. Experimentally, we identified that the storage space is not dependent on the file size, and utilization of the knowledge base expedites the search process. Of course, there are a number of limitations. We only conducted a very small scale experimentation. That is sufficient to show what are the differences between two approaches. However, it doesn't allow to judge what will happen for the fully fledged rollout of the solution. Also, we didn't consider what is the cost of maintaining the knowledge base in the distributed mode, and the knowledge base also could be one of the weak points of our solution, and it's further research is required to find the efficient way of maintaining the knowledge base in the large networks. Thank you very much. And if you want to look up more information, you can visit my website.
Okay, and anyone have a question?
So I just wondering how you control access of shared data in your system.
Hello, Janice, are you here?
No.
Janice, are you here?
Seems not.
Yeah, maybe. And Janice, maybe you can type your question, and maybe he will answer your question later.
Sure.
Okay, and now we will move to the final paper given by Elena Kafeza. The title is Legal Smart Contracts in Ethereum blockchain, linking the dots. Let's welcome. Elena is an associate professor in Zayed University.
Morning. My name is Eliana Kafeta, and I will present our research work on legal mass smart contracts in blockchain. Blockchain technology already has changed the way people interact by enabling transparency and eliminating third parties. And smart contracts play a key role in this. Smart contract is software code-based agreements that are autonomous and they are self-executive, and they can facilitate, validate, execute, and enforce the agreements. In this work, we are looking into a special case of smart contracts, the legal smart contract. Legal smart contract is expected to revolutionize the way that businesses are interacting, because by eliminating the third parties, they will allow for fast business transactions as well as for lower costs. So in this work, we are looking into legal smart contracts, and we are looking into the natural language legal contract and their connection to the smart contract, which is a program. Although it seems that legal smart contract is something that very much anticipated in the business world, there are a lot of challenges that still need to be addressed. For example, the business environment is a dynamic environment where changes are happening and agreements are changing. For example, contracts can be modified, a deadline can change. The quantity of the goods that are being delivered can be more or less. So several changes can happen during the lifetime of contract execution, and the problem is that blockchain is immutable. And it's very difficult for the time being to accommodate such changes. Moreover, because this automation in the contract has an irrevocable result, we need to create a solid methodology for the development of such applications. We need to have a friendly user interface, and we need to integrate the diversity of these technologies in a more systematic way that it is now, it exists now. So what is the contribution of our work? So we are proposing a system architecture that allows the user to interact and update contracts, take advantage of the blockchain properties. We are proposing the use of versioning system in order to handle blockchain immutability. And we also provide a methodology for the technology integration and for the development of such applications. We are building a prototype for a lendal agreement to show how our methodology can be applied. So when we are building legal smart contracts, we are proposing to have a four-tier architecture. We are proposing to have the presentation layer where, again, we have the interaction with the user, the business tier that holds the business logic of the contract, and then the data tier that has the data storage. We also propose to put a new tier, the blockchain tier, that will be responsible for the deployment and the execution of the legal contract. This is an outline of our system architecture. So we have the user interface, the presentation tier, so the user interacts. And what do we mean by interacts? The user creates, modifies, deploys, or confirms contracts. And this is through a friendly user interface. We know that contracts currently in the Ethereum usually are written in Solidity, and Solidity is translated to the bytecode that executes in the Ethereum virtual machine. And while an interface, the application binary interface, ABI, and the address of the contract are generated. So here, the contract manager, what he is doing, the contract manager implements the application logics, and whenever he wants to interfere or to interface with the deployed contract, he uses the ABI and the address of the contract in order to communicate. And the Web3 interface also allow us to create and deploy the smart contract. There are different storage approaches as well. When it comes to smart contract modification, we are proposing two issues. First of all, we are proposing the creation of a common smart contract for the data layer. So the data layer is going to be a small contract that we call data store, and thus all the data is going to be encapsulated in this object. So whenever we create a new smart contract or update a smart contract, we take the data from the data store smart contract and set the attribute values of the updated version of the smart contract. So we use the existing data from the previous contract in order to set the data for the updated contract. So this example here shows a minimal contract that we can create. We call it data storage, and this is that stores the data for the smart contract, and it's using actually a map. It maps the address of the smart contract using a map, and this map, what does? It stores the value, the key value pairs of the attributes and the values for the smart contract for this address. So if we create a new version of the smart contract, we can get all the data if we know the address of the previous one. With respect to the modification of the contract, we are proposing the versioning system. So the versioning system is support updates. Each smart contract is a derived contract of a base smart contract. The node smart contracts defines a node in a double linked list. Now this line of modifications becomes actually an evidence line that proves the changes that have been done in the contract. So in this way, and because all these contracts are linked and they are in the blockchain, this evidence can also be used as evidence in the court. So the contract manager sets the next the previous pointer to the smart contract whenever a new version of the smart contract is deployed, so that we can get the address. And of course, if we want to interact with the previous or the next contract, we also need to access the API. In this slide, we can see an action diagram for a legal contract in a blockchain for the case of a rental agreement. So we have the landlord is uploading the contract, is deploying the contract. The user logins as a tenant, and he confirms the agreement of the contract, and he pays the deposit. The moment the agreement is confirmed, the deposit is paid automatically to the landlord. Then automatically every month the tenant is paying the rent to the landlord. The landlord also later on can modify the legal contract, and he can upload a new contract and deploy this new contract. Then the tenant can confirm the modified contract or he can reject it. And if the tenant rejects the contract, then the previous contract is terminated as the new modified contract is initiated and the execution continues. Moreover, there are other clauses in the contract that can be activated. For example, the tenant can cancel the contract in the midway before the end of the contract, and as a remedy, he will pay a certain amount of the deposit automatically. So in this diagram, we see how all these aspects that we described in the previous slides are integrated in the context of an application. So as I said, in order to implement such an algorithm, we need to integrate several technologies: Solidity, Python, Solidity for the smart contracts, Python for the business logic, Web3 in order to interact with the Ethereum. And in our case study, as I just explained, we have a rental agreement where we provide a dashboard for the contract management, and we also provide modifications and functionality for contract modification, where the system automatically links the new contract to the old contract. We implemented this system by following the system architecture that I just presented, and as a result, managed to have this the system. These are some examples of screenshots of our system. And what are our conclusion? Our conclusion is that illegal smart contract is going to be a big application in the blockchain. It's going to change the way that business is conducted. It will lead to legal agreement automation. It will provide a methodology and the system architecture. In this work, we provide the methodology and the system architecture in order to tackle this problem, and with user case study to show how it is applied for a specific case. In our future work, we are using chatbots to mediate contract modifications and conflicts, and we are considering to use blockchain to ensure trust and transparency in the mediation process. Thank you.
Okay, and anyone has a question?
So I may have a question. So hi, Ariana. Thanks for this nice work. So maybe I missed something. So what's special for a legal smart contract, and also make it different from those normal smart contracts?
Is that they do have a lot of restrictions that are not there in the traditional contracts. For example, the legal smart contract has to be connected to the traditional paper contract in order to have some meaning and some effect, because we need to combine the smart contracts to a legal document. And that creates a lot of issues because, for example, if we want to have, to use, as we said, for example, we use the modification in order to create a linked list of contracts. And this can be used in forensics when there is a dispute. So the question comes with a legal contract is how can we use the blockchain technology as forensics and as for to have some legal binding power in the concept of the legal framework. So the issue first is how can we make sure that these things are connected and how we can keep evidence of the steps that we are doing, which is not the case in traditional smart contracts. We don't really care. We just care to do the job. And the next thing is that one of the big problems when you create this kind of application is that there is not just a sequence of steps that you can follow. Still developing contracts in blockchain and using also things for Python. And as the previous people that presented said, some things can be stored inside the blockchain. Some things can be stored outside the blockchain. So there is not a data flow and a flow of how to implement such an application. So I think one of our contribution also is that for people who want to just do legal applications, and we provide some ideas of what things should be where. So I think this is also important.
Okay, yeah, thank you.
Okay, and there is still another question from Zepeng. He said, is the contract manager a centralized node?
Yes, so the contract manager is outside the blockchain. Because we want, that is what I just said, we want to create an application that is going to be fast, it's going to be user-friendly, and it's going to have the business logic. But at the same time, from the blockchain, we want to keep the evidence, only the part that will make sure that these were the contracts and these were the modifications. So in case we go to court, we can make sure that all the things that we did in the business logic, there is evidence to support. So that's why we create these two different tiers. Whatever you want to do just for having user-friendly applications or create your own application, how to confirm, how to create a contract, you can put it outside the blockchains. And when it comes to evidence, these transaction smart contracts have to be inside the blockchain.
Okay, thank you. Any other question? Okay, if there is no other question, and we will thanks Elena, and close this technical session. And Jian, do you want to say something for this workshop?
Just say thank you all for the participation, and also hopefully we can see you next year in person. Okay, so thank you again, and have a good day for those in Europe or in USA, and have a good night for those in Asia. Thank you all for the participations.
Yeah, thanks to all the audience.
Okay, thank you.
Thanks. Bye-bye.
Bye-bye.